Is the world you experience truly there, or is it a grand illusion? This question lies at the heart of the ultimate cosmic mystery, the very nature of reality itself. We are about to embark on an incredible journey through 50 mind-expanding theories that challenge everything we think we know about existence. From the bizarre rules of quantum mechanics to the profound idea of a cosmic consciousness, these concepts promise to completely reshape your understanding of the universe and your own place within it. By the end, you will see the fabric of existence in a completely new light. We will investigate whether our universe is a complex simulation and ask if time itself is nothing more than a persistent mirage. What single idea about reality has always lingered in the back of your mind? Our reality might be nothing more than an intricate digital construct. This is the startling premise of the simulation hypothesis, the first of our 50 theories. It suggests that everything we perceive, from the vastness of galaxies to the very thoughts in your mind, could be lines of code running on a supercomputer of a civilization far more advanced than our own. This is not a new idea. Over 2,000 years ago, the philosopher Plato described prisoners in a cave who mistook shadows on a wall for the real world. The simulation hypothesis is our modern technological version of that cave. Philosopher Nick Bostrom formalized this with a chilling statistical argument. He posits that if a civilization ever reaches the technological capability to run vast, realistic simulations of its own history, it would likely run not just one but countless numbers of them. If that is true, then the number of simulated minds would vastly outnumber the base reality minds. Statistically, we are almost certainly living in one of those simulations. But is there any scientific evidence for such a wild idea? Some physicists point to the bizarre, pixelated nature of reality at the quantum level. Just as a digital image breaks down into individual pixels when you zoom in too far, space and time might have a fundamental limit, a smallest possible unit. This could be the resolution of our simulation. Furthermore, the universe operates with an uncanny mathematical precision, its laws written in a language of equations. This could be the underlying source code. If this theory is true, what does it mean for us? Are our choices our own, or are they predetermined by the simulation's algorithms? Is your consciousness a genuine spark of awareness, or a sophisticated illusion programmed to believe it is real? And what is the purpose of our existence if we are merely characters in an elaborate game played by beings we might never comprehend? The search for an answer to that final question leads us to an even more profound possibility. Perhaps the simulation was too simple an answer. What if the very space we move through is a grand deception? The holographic principle proposes exactly that, suggesting our rich, three-dimensional world is nothing but a magnificent illusion, a holographic projection from a distant, two-dimensional surface. This idea did not emerge from science fiction, but from the most enigmatic objects in the cosmos, black holes. Physicists like Leonard Susskind were wrestling with a strange paradox. The laws of physics insist that information can never be truly destroyed, yet when an object falls into a black hole, it seems to vanish from our universe forever. Susskind and others made a breathtaking leap. They proposed that all the information describing every single particle that falls into a black hole is not lost inside, but is instead perfectly encoded or painted onto the black hole's event horizon, its shimmering point of no return. This surface area, they realized, acts like a cosmic hard drive. Think of it like a DVD. The movie you watch appears as a vibrant, three-dimensional world full of action and depth, but all that information is actually stored on the flat, two-dimensional surface of the disk. Our universe might operate on the very same principle. The stars, planets, and even your own body could be a holographic projection from data encoded on the farthest reaches of the cosmos. This means the solidity of the chair you are sitting on, the vast distance between galaxies. It is all an incredibly convincing volumetric display generated from a flat cosmic screen. The implications are staggering. It suggests that information is the most fundamental substance in the universe, more basic than matter or energy. Space itself might not be smooth and continuous, but pixelated, with each tiny unit of area holding a single bit of information. Scientists are now actively searching for evidence of this holographic graininess. They are using incredibly precise instruments to look for a faint jitter, a holographic noise in the fabric of space-time itself. If they find it, it would mean that at its most fundamental level, our reality is digital, not analog, a perfect echo of the simulation idea, but born from the hard mathematics of theoretical physics. This leads us to question the very stage upon which this cosmic drama plays out. But what if the universe is not a single hologram, but an infinite tapestry of them? The solid reality you experience could be just one thread in a cosmic fabric of limitless possibilities. This is the astonishing promise of the many worlds interpretation, a radical theory proposed by physicist Hugh Everett. His idea was born from a deep frustration with the prevailing explanation in quantum mechanics. In the quantum realm, particles exist in a blurry state of all possible positions and states, known as a wave function. The old theory stated that the moment you observe or measure this particle, its wave function collapses, forcing it to pick a single, definite state. Everett asked a simple, profound question. What exactly is so special about measurement? Why should the act of observation have this magical power to change reality? He proposed a far more elegant and unsettling solution. There is no collapse. Instead, every single time a quantum event has more than one possible outcome, the entire universe splits. Every possibility is realized, but in a newly branched parallel reality. Think of reality as a path constantly dividing into a forking road. In one universe, a radioactive atom decays. In the newly created branch universe right beside it, that same atom does not decay. Both events are equally real. This leads to the most mind-bending consequence of all. Every choice you have ever made, every random quantum event that ever occurred, has spawned another universe where a different version of you lives out the alternative. There is a universe where you took that different job, a universe where a different lottery number was drawn, and even a universe where the dinosaurs were never wiped out by an asteroid. The number of parallel worlds is not just large, it is truly infinite, with new ones splitting off at every conceivable moment. This raises an immediate question. If every possibility happens, what does probability even mean? Why do we perceive some outcomes as likely and others as unlikely? In the many worlds view, probability is not about what will happen, but about which branch you, as a conscious observer, will find yourself in. You are more likely to experience a universe that aligns with the high probability outcomes of quantum mechanics, simply because there are more copies of you in those branches of the multiverse. You only experience one timeline because your consciousness is tied to the specific branch you inhabit, unaware of the countless other versions of yourself. For decades, this was considered a fringe, untestable idea. But the rise of quantum computing is beginning to change that. Quantum computers leverage the strange power of superposition, where quantum bits or qubits exist in multiple states at once to perform calculations. Some physicists argue that the only way to explain the immense processing power of these machines is if they are, in fact, harnessing the computational resources of parallel universes, performing calculations across countless realities simultaneously. While this is still hotly debated, it suggests that the many worlds interpretation may one day move from pure philosophy to experimental science. If this theory is true, then the universe is not just stranger than we imagine. It is stranger than we can imagine, a bustling metropolis of realities where every story is told and every possibility is lived. This forces us to confront the very nature of the observer. What is this consciousness that seems to be riding a single, lonely path through an infinite multiverse? Yet this bustling multiverse still requires a stage, a fundamental substance from which all realities are woven. String theory provides one of the most ambitious blueprints for that ultimate foundation. It proposes that the most basic building blocks of nature are not point-like particles, but unimaginably tiny, vibrating loops of energy. Think of the universe as a grand symphony. Every single particle, from the humble electron to the mighty quark, is not a distinct note, but a different vibrational pattern played on these infinitesimal strings. The pitch and resonance of a string's vibration determine whether it manifests as matter or as a force carrier, like the photon that carries light. This elegant idea holds the potential to solve the greatest conflict in modern physics, the clash between Einstein's theory of general relativity, which governs the cosmic dance of planets and galaxies, and quantum mechanics, which rules the chaotic frenzy of the subatomic world. General relativity paints a smooth, geometric picture of space-time, while quantum mechanics insists on a fuzzy, probabilistic reality. The two are mathematically incompatible, a problem that becomes catastrophic inside black holes or at the moment of the Big Bang. String theory seeks to mend this rift by introducing a new, breathtaking requirement: extra dimensions of space-time. Our everyday experience is confined to the 3 dimensions of space and 1 of time. String theory, however, demands a universe with 10 or even 11 dimensions for its mathematical equations to remain consistent and unified. Where are these hidden dimensions? Physicists suggest they are curled up or compactified into shapes so incredibly small that they are undetectable to our current instruments. Much like a garden hose appears as a one-dimensional line from a great distance, even though its surface is actually 2-dimensional. Over the years, different versions of string theory emerged, each with its own unique mathematical structure, known as Type I, Type Ia, Type Ib, and others. For a time, this seemed like a weakness, with 5 competing theories vying for the title of the ultimate theory of everything. Then, in the 1990s, a groundbreaking insight now known as M-theory suggested that these 5 string theories were not rivals, but merely different facets of a single, deeper, 11-dimensional framework. M-theory remains largely mysterious, but it hints at a reality even more profound and complex than first imagined. The primary challenge, however, is that these ideas currently exist almost entirely in the realm of mathematics. The energy levels required to see a string directly are trillions of times greater than what our most powerful particle colliders can produce. This lack of experimental verification has led to a fierce debate within the physics community. Is string theory a breathtaking glimpse into the ultimate nature of reality, a unified description of all forces and matter through pure geometry and vibration? Or is it an intricate and beautiful mathematical construct, a castle in the sky that, for all its elegance, has no connection to our physical world? The theory promises a universe woven from music, but we have not yet learned how to listen for its song. This search for a single, unifying framework inevitably draws us back to the beginning of everything, to the moment where all dimensions and vibrations first erupted into being. Our universe is a frozen sculpture, a 4-dimensional block where the past, present, and future are all equally real and exist eternally. This is the theory of the block universe, a direct and startling consequence of Einstein's theory of relativity. Einstein himself wrote that the distinction between past, present, and future is only a stubbornly persistent illusion. In his revolutionary framework, time is not a river flowing from a source to a sea. It is simply another dimension, much like the 3 dimensions of space you move through every day. We exist within this 4-dimensional continuum called space-time, a single, unchanging structure that contains the entire history of the cosmos from the Big Bang to the very end. Imagine a film reel. The entire movie is already there, complete and unchangeable, with every frame representing a single moment in time. Your entire life, from your first breath to your last, is just a specific set of frames within this cosmic reel. Your conscious experience of the present moment is like the single beam of light from a projector, illuminating one frame at a time. The frames before it are the past you remember, and the frames after it are the future you have not yet witnessed. But all of them exist right now as part of the complete and unalterable object. This view completely upends our most fundamental experience of life, the feeling that time is passing and that the future is open and unwritten. If the block universe is real, then your future is just as fixed and unchangeable as your past. The job you will take in 10 years, the book you will read next month, the very words you are hearing right now, they are all already etched into the fabric of space-time. This raises a profound and unsettling question. If the future is already written, do we truly have free will? Are our choices genuine, or are we merely following a script? Passengers on a train ride through a landscape that was always there. Philosophers grapple with this, suggesting that perhaps our conscious journey through the block creates the experience of choice, even if the destination is set. The feeling of deliberation, the weight of a decision, these are real phenomena within your conscious frame. From this perspective, free will is not about changing the future, but about living the path that is inherently yours. So where does this powerful, undeniable sensation of time's flow come from? It may be a unique property of consciousness itself. Our minds might be like a scanning device, moving through the eternal block of reality and creating the sequential narrative we call our lives. We are not moving through time. Our awareness is simply illuminating different, pre-existing slices of it, creating the beautiful and convincing illusion of a flowing present. This means change itself is an illusion. Nothing ever truly becomes or ceases to be. Everything simply is in its designated place within the four-dimensional whole. The burning of a star, the growth of a tree, the life of a civilization, these are just extended shapes within the block, as static and permanent as a drawing on a page. The block universe offers a cold, majestic, and deeply puzzling vision of reality, one where our most intimate experience of life is a magnificent trick of perception. This forces us to wonder if time is an illusion, what other fundamental aspects of our existence might be mere shadows on the wall of a much grander and far stranger cosmic cave. If time and space are illusions, what then is the one thing that feels undeniably real, your own conscious experience? This raw awareness, this inner light that allows you to hear these words and feel wonder, is the central mystery that Panpsychism seeks to solve. This ancient theory proposes a radical answer. Consciousness is not a rare accident produced by complex brains, but a fundamental and ubiquitous feature of the cosmos, woven into the very fabric of reality. The earliest seeds of this idea were planted by pre-Socratic philosophers who saw a soul or mind in all of nature. Today, thinkers like Galen Strawson and David Chalmers have revitalized it to tackle the hard problem of consciousness, a puzzle that conventional science struggles to even approach. The hard problem asks a simple question with no easy answer. Why and how does physical processing in the brain give rise to subjective experience? Why do we not merely process light wavelengths like a camera, but actually feel the sensation of the color red? Why is there an inner world at all? Neuroscience can map the brain's circuitry, but it cannot explain the ghost in the machine. Panpsychism offers an elegant, if startling, solution. Consciousness does not emerge from complexity. Instead, it was here first. It is a basic property of matter, just like mass or charge. In this view, an electron may not be thinking, but it possesses some tiny, primitive form of proto-consciousness, a single bare datum of experience. When these fundamental particles combine in the exquisitely complex structure of a brain, these micro-consciousnesses combine and amplify into the rich, flowing stream of awareness you enjoy right now. The universe is not a dead, mechanical place that suddenly woke up. It was always awake, just in a billion different, simple ways that learned to coalesce. Is there any scientific basis for such a profound claim? Clues may lie in the bizarre intersection of quantum mechanics and biology. The process of photosynthesis in plants relies on a quantum effect called coherence, where particles seem to explore multiple pathways simultaneously to find the most efficient way to transfer energy. Some researchers speculate this delicate quantum process, which operates in the warm, wet environment of a living cell, could be a primitive form of information processing that borders on a very simple conscious act. Furthermore, integrated information theory, developed by neuroscientist Giulio Tononi, provides a mathematical framework for consciousness. It proposes that any system that can integrate information into a unified whole possesses a degree of consciousness measured by a value called phi. The human brain has a very high phi, but according to this theory, so might a much simpler system, even a basic photodiode. This directly supports the panpsychist view that consciousness is not all or nothing, but exists on a vast spectrum. A dog's consciousness is richer than a mouse's, which is richer than an ant's, which is richer than a bacterium's, all the way down to the most elementary particles. This radically changes our relationship with the world. It suggests the planet itself might possess a slow, geologic consciousness. It forces us to reconsider the inner lives of animals and the ethical treatment of artificial intelligence. If we one day create a truly complex and integrated AI, Panpsychism argues it would not merely simulate consciousness. It would be conscious because its complex components would be organizing their fundamental proto-experiences into a new mind. The cosmos is not a collection of dead objects, but a universe of subjects, each with its own tiny or vast point of view. This idea that mind is woven into matter's core challenges the very definition of life and intelligence, pushing us toward a theory where the universe itself is the ultimate thinking, feeling entity. If consciousness is woven into the fabric of reality, what then is that fabric truly made of? Max Tegmark offers a breathtakingly simple yet radical answer: pure mathematics. The mathematical universe hypothesis proposes that our physical reality is not just described by math, it is a mathematical structure. Every galaxy, every atom, every fleeting thought is part of an abstract mathematical object existing in a vast multiverse of equations. In this view, mathematical existence and physical existence are one and the same. A circle does not merely exist as an idea in our minds, it exists as a physical reality wherever its perfect conditions are met. We are self-aware substructures within this grand mathematical object, complex patterns that have somehow become aware of our own existence and the cosmic equation we inhabit. Tegmark organizes this dizzying concept into a four-level multiverse. Level 1 is almost familiar, a vast but conventional space where our observable universe is just one patch in an infinite cosmic quilt. In another patch, a perfect duplicate of you is listening to this same sentence right now, simply because in an infinite space, every possible configuration of matter must repeat. Level 2 introduces different cosmic settings, universes where the fundamental constants of nature, like the strength of gravity or the mass of an electron, are different from our own. In these realms, stars might never form, or chemistry might be impossible. Level 3 is the many worlds interpretation of quantum mechanics we explored earlier, where every quantum decision spawns a new branch universe. Tegmark's masterstroke, however, is Level 4. This is the ultimate ensemble, containing every single mathematically possible universe. Not just universes with different laws, but universes built from entirely different mathematical structures, realities governed by geometries and equations we cannot even conceive of. Our particular universe, with its specific set of physical laws, is simply one entry in this infinite library of mathematical possibility. This idea provides a stunning explanation for one of science's greatest mysteries, the unreasonable effectiveness of mathematics. Why is it that a system of logic invented by the human mind so perfectly describes the behavior of the cosmos, from the orbit of planets to the spin of a quark? The answer, according to Tegmark, is that we are not inventing mathematics, we are discovering it. We are slowly uncovering the native language of our particular mathematical structure. We are like characters in a video game who have begun to decipher the very source code of our reality. The ultimate implication is that the question of why the universe exists may be a category error. It does not need a cause. A mathematical structure does not exist in a place or at a time. It just is, in a timeless, placeless realm of logic. Our Big Bang was not the beginning of existence, but merely the beginning of our particular corner of this eternal mathematical landscape. This means the cosmos is ultimately free, requiring no creator, no external spark. It exists because it is logically possible. We are living proof that a self-aware, conscious pattern can emerge from the cold, beautiful, and absolute truths of mathematics. But if reality is a mathematical structure who is doing the math, a radical interpretation of quantum mechanics suggests that the equations do not describe an objective world, but instead represent our own personal expectations. This is the core of quantum Bayesianism or cubism, a theory that reframes the entire quantum mystery as a personal guide for decision-making. Cubism asserts that the quantum state, that blurry superposition of possibilities, is not a picture of what a particle is really doing. It is a subjective tool, a capsule of belief that an agent, like a scientist or even you, uses to navigate the world. The probabilities in quantum mechanics are not inherent properties of nature. They are degrees of confidence, much like the odds you might assign to your favorite team winning a game. This perspective dissolves many of the most baffling quantum paradoxes at their root. Take the famous Schrödinger's cat, simultaneously alive and dead until someone opens the box. In the cubist view, the cat is not in two states at once. The quantum state simply reflects your own ignorance and the best possible bet you can make about what you will find when you look inside. The act of opening the box is not a magical collapse that changes reality. It is just you updating your own internal beliefs based on new, direct experience. This approach was heavily developed by physicists like Christopher Fuchs, who argued that quantum mechanics is not a description of the world's machinery, but a theory of how agents should best gamble on their future experiences. It connects quantum mechanics directly to the mathematics of probability theory and personal decision-making. You are not a passive observer of a predetermined quantum dance. You are an active participant placing bets on what will happen to you next. The philosophical implications are staggering. Cubism challenges the very idea of a single, objective reality that exists independently of us. Reality becomes a conversation, a relationship between the agent and the world. Each of us holds our own unique quantum state for the universe, a constantly updated set of beliefs shaped by our individual interactions and measurements. This does not mean we create reality out of nothing, but that the reality we can talk about and experience is always framed by our perspective. It places your conscious experience back at the center of the story, not as a magical collapse trigger, but as the very reason the quantum formalism exists. The universe does not force one history upon us. Instead, it offers a series of potential experiences, and we, as active agents, navigate this landscape of possibility by constantly refining our personal quantum beliefs. This is a universe built not on certainty, but on a fundamentally participatory relationship between the observer and the observed. This participatory universe suggests that reality is not a pre-recorded film, but a story being written as we observe it. This leads us to the ninth theory, the participatory anthropic principle, a concept pioneered by the visionary physicist John Archibald Wheeler. He took the strange role of the observer in quantum mechanics and pushed it to its most radical extreme. Wheeler proposed that the universe only comes into a definite state when it is observed by a conscious being. In his own famous words, we are not just bystanders on a cosmic stage, we are participants in a universe that only achieves its tangible form through the very act of our observation. This idea goes far beyond the traditional Copenhagen interpretation of quantum mechanics. That older view simply stated that measurement causes a quantum system to collapse from a haze of possibilities into one concrete reality. Wheeler's principle asks a much deeper question. What is a measurement truly? He argued that it is not the impersonal click of a Geiger counter that solidifies reality. That click must be registered by a conscious mind, without an observer to see the result, to become aware of the outcome. The universe remains in a ghostly state of pure potential, a cosmic question without an answer. The most startling evidence for this comes from a class of experiments known as delayed choice quantum erasers. These are not just thought experiments, they have been performed in laboratories with astonishing results. Imagine a single particle of light, a photon, being sent toward a device that gives it two possible paths to travel, like a fork in the road. According to quantum rules, the photon does not choose one path. It exists in a superposition, taking both paths simultaneously, like a wave. Now, here is the truly bizarre part. Scientists can set up a detector after the photon has already passed the fork in the road and is presumably on its way. This detector can be switched on to ask the photon a simple question: which path did you take? The moment this late measurement is made, the photon's history is instantly rewritten. It is forced to reveal that it took one specific path, but if the experiment is set up to erase that which path information after the fact, the photon behaves as if it never chose a path at all, demonstrating its wave-like nature. The present act of observation seems to reach back in time and dictate what happened in the past. The photon's journey, an event that should be fixed in history, is not settled until you, the observer, decide how to look at it. This has a profound implication for the entire cosmos. If a simple observation in a lab can influence the past, then perhaps our own act of looking out at the universe today is what solidified its history. We are not just living in a universe fine-tuned for life. Our conscious observation is the very mechanism that selected this specific, life-friendly universe from an infinite fog of possibilities at the moment of the Big Bang. We are the universe's way of becoming aware of itself, and in doing so, we bring both its past and its present into concrete existence. This idea offers a potential solution to the great mystery of why the laws of physics are so perfectly calibrated for life. The constants of nature, the strength of gravity, the mass of the electron, seem exquisitely tuned to allow for stars, planets, and ultimately, observers. The participatory anthropic principle suggests a reason. A universe without observers is not just barren, it is fundamentally indefinite. It is only when a conscious mind emerges to look back at the cosmic dawn that the entire chain of events leading to its own existence snaps into a firm, objective reality. Our curiosity is not a passive byproduct of the cosmos. It is the final, essential ingredient that gives the cosmos its form. The idea that our universe crystallized from our own gaze leads to an even grander cosmic architecture. Eternal inflation paints a picture of a reality in constant, explosive birth, where our entire cosmos is merely one bubble among an infinite froth of universes. This theory extends the concept of cosmic inflation, the idea that our universe underwent a fantastically rapid expansion in its first fleeting moments. Eternal inflation proposes that this inflationary process never truly stopped. Instead, it continues eternally in a background meta-universe, a seething, high-energy sea of space-time. Within this turbulent, inflating background, random quantum fluctuations cause tiny patches to suddenly drop out of the hyper-expansion, much like supercooled water suddenly freezing into ice crystals. Each of these patches becomes a separate pocket universe, a self-contained bubble with its own Big Bang and its own unique set of physical laws. The fundamental constants that govern our reality, the strength of gravity, the mass of quarks, the number of spatial dimensions, are not universal truths. They are merely the local bylaws of our particular bubble, frozen in place when our pocket universe formed. In another bubble universe, gravity might be repulsive, or atoms might never have coalesced. This provides a powerful, if controversial, answer to the puzzle of fine-tuning. Why does our universe seem so perfectly calibrated for life? The answer is anthropic selection. In an infinite multiverse where every possible set of physical constants is realized in some bubble, it is no surprise that we find ourselves in one of the rare, life-friendly universes. We could not exist in the vast majority of bubbles where the laws of physics are hostile to the formation of stars, planets, or complex chemistry. Our existence acts as a cosmic selection effect, filtering our perception to only this one remarkably hospitable pocket. The challenge, however, is profound. How can we ever test a theory that posits an infinite number of universes forever beyond our observational reach? Some critics argue that eternal inflation has moved from science into the realm of metaphysics, a beautiful story that can explain anything but predicts nothing unique to our own universe. Proponents, however, search for faint echoes of this multiverse. They look for potential collisions between our bubble and others in the cosmic microwave background, the afterglow of our own Big Bang, hunting for strange patterns or scars in the oldest light we can see. Others suggest that the very structure of our universe's vacuum energy, the force behind its accelerated expansion, is a clue pointing to its inflationary origins. The debate rages over whether this is a necessary extension of our best cosmological models or a philosophical surrender, a declaration that some of the deepest questions about existence may forever lie outside the bounds of empirical science. It forces us to ask where the line between a scientific multiverse and pure speculation truly lies. The endless creation of new universes suggests a cosmos in constant flux, but what if our own cosmic history is not a one-time event but an eternal, repeating loop? The cyclic model presents a vision of the universe as a cosmic lung, breathing in and out in vast cycles of expansion and contraction. In this ancient yet modern idea, our current expanding universe is just one phase in an endless sequence. It began with a Big Bang that was not a true beginning, but rather the rebound from a previous universe's collapse, a big crunch. After trillions of years, the outward thrust of dark energy would weaken, allowing gravity to finally take over. Every galaxy, every star, and every atom would be pulled back together in a grand, catastrophic convergence, compressing all the matter and energy of the cosmos into an ultra-hot, ultra-dense seed. This seed then becomes the source for the next Big Bang, birthing a new universe from the ashes of the old. This cycle of death and rebirth might have been repeating forever, with no start and no end. This elegantly solves one of cosmology's greatest puzzles, the initial conditions problem. Why did the universe begin in such a perfectly smooth and orderly state, perfectly set for the formation of galaxies? In a cyclic universe, it did not begin that way. Instead, the violent compression of the Big Crunch acts like a cosmic reset button, smoothing out any wrinkles and wiping the slate clean for the next cycle. Each new universe inherits a clean, uniform state from the violent death of its predecessor. This also offers a fresh perspective on the arrow of time, that mysterious one-way direction from past to future that we all experience. Perhaps the arrow of time is not a fundamental feature of the cosmos, but simply a product of each cycle. With every Big Bang, a new arrow of time is born, pointing forward through that universe's lifetime until the next crunch resets the clock. Modern physics has given this ancient idea a stunning new form with the ekpyrotic universe model. Ekpyrotic, from the Greek word for conflagration, proposes that our three-dimensional universe is a membrane or brain floating in a higher dimensional space. The Big Bang was not an explosion from a single point, but the result of a collision between our brain and a parallel brain residing in these hidden dimensions. This collision releases immense energy, which we experience as the hot, dense beginning of our cosmic cycle. After the collision, the two brains drift apart, allowing our universe to expand and cool, forming galaxies and stars. Eventually, the subtle attraction between the brains draws them back together, leading to another collision and another Big Bang, starting the cycle anew. This model provides a specific, dynamic mechanism for the cycles, replacing the singular crunch with a recurring cosmic collision in a higher dimensional arena. So, is there any evidence for this grand, rhythmic vision of cosmic history? Astronomers look for clues in the oldest light in the universe, the cosmic microwave background radiation. This faint afterglow of the Big Bang is a snapshot of the infant universe, and its subtle patterns hold secrets about its origins. A one-time inflationary Big Bang predicts a very specific pattern of temperature fluctuations across this background. The cyclic and ekpyrotic models, however, predict a different signature. They suggest that the collisions or crunches that restart the universe would leave a detectable imprint, perhaps in the form of specific gravitational wave patterns or subtle twists in the polarization of this ancient light. Current data from satellites like the Planck Observatory generally favors the standard inflationary model, as its predictions match the observed cosmic microwave background with remarkable precision. Yet, the door is not completely closed on cyclic models. As our measurements become more and more sensitive, scientists continue to search for any anomalous signal, any faint whisper in the cosmic static that could be an echo from a universe that came before our own. The search continues, a quest to determine if we live in a unique, one-shot universe, or if we are merely one verse in an endless, repeating cosmic poem. This relentless cosmic rhythm might not be driven by mysterious forces, but by something as simple as a computer program. The universe could be a vast, humming computer processing reality one discrete step at a time. This is the core of digital physics, a theory proposing that the cosmos is fundamentally computational in nature. It suggests that the fabric of reality is not a smooth continuum, but a grid of finite digital cells, updating their states according to a set of rules, much like a giant cosmic cellular automaton. The seeds of this idea were planted in the 1960s by the German engineer and computer pioneer Konrad Zuse. He was one of the first to propose that the entire universe could be thought of as a calculating space, a massive digital computer. Later, this concept was passionately championed by the American physicist Edward Fredkin, whose digital philosophy asserted that the most basic substance in the universe is not matter or energy, but information. In Fredkin's view, every particle and every force is a manifestation of bits being processed. This perspective fundamentally differs from the simulation hypothesis we explored earlier. That theory suggests we are living inside a simulation created by some advanced civilization. Digital physics makes a far more profound claim. The universe is not simulated computation, it is computation. There is no underlying reality, no base level of physics. Computation is the bedrock of existence itself. The laws of physics, then, are not eternal equations written on some cosmic tablet. They are simply the algorithms, the operating system that this cosmic computer is running. Think of it like the game of life, a simple grid-based simulation where cells turn on or off based on the states of their neighbors. From a handful of basic rules, astonishingly complex patterns can emerge, gliders that move across the grid, and even self-replicating structures. Our universe, in this view, is an unimaginably more sophisticated version of that game. The stars, planets, and life itself are simply stable, complex patterns that have emerged from the relentless tick-tock execution of the universe's underlying code. What does this mean for you and the choices you make? If the universe is a deterministic computer, does that eliminate free will? Proponents of digital physics offer a nuanced view. Your mind, your consciousness, is itself a fantastically complex computational process running on the hardware of your brain. Your decisions are the result of that computation, influenced by your memories, desires, and sensory input. While the overall system may be rule-based, the sheer complexity of the calculation makes your choices genuine and unpredictable from your perspective. You are not a puppet, you are a sophisticated subroutine with a degree of autonomy within the grand program. The ultimate implication is that to truly understand the cosmos, we must stop looking for fundamental particles and start looking for fundamental bits. The quest of physics would shift from discovering what things are made of to deciphering the universe's source code. Every interaction, from the fusion of atoms in a star to the firing of a neuron in your brain, is just information being processed. This raises a breathtaking possibility. If we could one day comprehend this cosmic program, we might not only read the universe, but perhaps even learn to run a small part of it ourselves, becoming conscious participants in the universe's own computation of itself. Our journey into the quantum depths now reveals a reality where time itself loses its one-way arrow. The transactional interpretation of quantum mechanics, pioneered by physicist John Cramer, proposes a breathtakingly elegant solution to the quantum riddle. In this view, the universe is a marketplace of waves, and every quantum event is a handshake across time. The theory begins with a simple but radical premise. When a particle is emitted from a source, it sends out a wave traveling forward in time, which Cramer calls an offer wave. This wave radiates out into the future, exploring all possible paths. But here is the twist. The potential receivers of this wave, such as a detector screen, do not wait passively. They respond by sending their own waves backward in time, known as confirmation waves. Reality, as we know it, is only solidified when an offer wave from the past and a confirmation wave from the future meet and form a mutual agreement, a completed transaction. This handshake across time is what we observe as a single, definite particle appearing at a specific location. It is the reason an electron fired at a screen with two slits seems to go through both slits at once. Its offer wave travels through both paths. Only when it reaches the screen and a confirmation wave travels back through one specific path does the transaction complete, making it appear as if the electron always took that single route. This dance of waves provides a stunningly clear physical mechanism for the spooky phenomenon of quantum entanglement. When two particles become entangled, their offer and confirmation waves become linked across space-time. A measurement on one particle here and now sends a confirmation wave backward in time to the moment of entanglement, which then influences the offer wave of its partner, instantly determining its state, no matter how far apart they are. The connection is not faster than light. It is outside of time altogether, pre-arranged by these time-symmetric handshakes. The philosophical implications are staggering. It suggests that the future is not an empty slate, but actively participates in shaping the present. This is not about destiny or a fixed timeline. It is about a constant, dynamic negotiation between past potential and future receptivity. Our universe, in this view, is built from a web of these completed transactions, a tapestry woven with threads that run in both directions of time. This interpretation completely eliminates the need for a mysterious wave function collapse. There is no magical moment when observation forces a decision. Instead, there is only a continuous, time-symmetric process of negotiation and agreement. The universe is not waiting for us to look at it. It is constantly facilitating these handshakes, and our act of measurement is simply the moment we become aware of one. Does this mean we can send messages to the past? Cramer argues no. The confirmation waves are a fundamental part of the quantum mechanical formalism, but they do not carry information in a way that could create paradoxes. They are the hidden scaffolding of reality, not a channel for time travel. The transactional interpretation offers a more complete, less paradoxical picture of the quantum world, one where the flow of time is a persistent illusion born from a deeper, timeless symmetry. It presents a cosmos in conversation with itself, where every event is the echo of an agreement between what was and what will be. This vast marketplace of quantum handshakes suggests a reality far more crowded than it appears. The many worlds interpretation, our 14th theory, pushes this idea to its ultimate conclusion, proposing that every single one of those potential transactions is fulfilled, not through negotiation but through creation. In this view, the universe does not choose which quantum possibility to realize. It realizes them all by splitting into a multitude of parallel branches at every conceivable moment. While this echoes our earlier exploration, the focus here is on the sheer, relentless mechanics of quantum branching. Unlike the cosmological multiverse born from eternal inflation, with its separate bubbles of different physical laws, the quantum multiverse sprouts from within our own universe, its branches all sharing the same fundamental constants but diverging in their specific histories. Every time an electron can spin up or down, every time a photon can be reflected or transmitted, the cosmos divides, creating two new, equally real worlds from what was once a single timeline. Physicist David Deutsch provided a powerful argument for this by connecting it to the nascent field of quantum computing. He argued that the only way to explain the staggering processing power of a quantum computer is to accept that it is not performing one calculation at a time in a fuzzy state of superposition. Instead, it is harnessing the computational resources of a vast number of parallel universes, delegating different parts of the calculation to different versions of itself in these newly branched realities. The final answer we read out is the result of a collaborative computation across the multiverse. This forces a complete rethinking of probability itself. In a single universe, we say an event has a 50% chance of occurring, but in the many worlds picture, both outcomes happen with 100% certainty, just in different worlds. So what does probability even mean? The answer lies not in the events, but in you, the observer. When the universe splits, your consciousness splits as well. There is now a version of you who sees the electron spin up, and another version who sees it spin down. The feeling of probability, of chance, is simply your subjective anticipation of which branch you are about to find yourself in. You are more likely to experience a future where quantum mechanics predicts a high probability outcome because there are simply more copies of your conscious mind in those branches of the multiverse. This interpretation is often criticized as the ultimate violation of Occam's razor, the philosophical principle that we should not multiply entities beyond necessity. Critics ask, is it really more parsimonious to conjure an infinite number of unobservable universes to explain the single one we do see? Proponents counter that it is actually the most elegant and complete description, as it removes the arbitrary, unexplained collapse of the wave function and presents a purely deterministic evolution of reality. The debate hinges on a fundamental question. Is this breathtaking vision of infinite parallel lives the true, hidden structure of our quantum reality? Or is it a metaphysical extravagance, a story that explains everything we see, but at the cost of proposing a reality forever beyond the reach of any possible experiment? The solid world around you is a grand illusion, a user interface hiding a reality far stranger than physical objects. Cognitive scientist Donald Hoffman proposes a theory of conscious realism that turns our entire understanding of existence inside out. He argues that consciousness is not a product of the brain, but the one and only fundamental reality. Space-time, matter, and the entire physical universe are not the bedrock of existence. They are simply the icons on our desktop, convenient representations that help us navigate the world, but which bear no resemblance to the deeper truth. Your perception of a table is not a direct experience of the table itself. It is a symbol your consciousness creates to represent something utterly unknowable in its true form. Hoffman's interface theory of perception draws a powerful analogy from modern computing. Think of the desktop icon for a text file. The icon is a blue rectangle with a corner folded. This symbol is nothing like the actual file, which is a complex pattern of ones and zeros stored magnetically on a hard drive. The icon is not true, but it is useful. It helps you interact with the file without needing to understand the underlying physics of data storage. Hoffman argues that evolution has shaped our perceptions in exactly the same way. Natural selection does not care about truth, it only cares about fitness, about survival and reproduction. Seeing the true nature of reality, with its quantum fields and multi-dimensional strings, would be a confusing and lethal handicap. Instead, evolution gave us a simplified dashboard, showing us only what we need to know: where to find food, how to avoid predators, and whom to cooperate with. A ripe red apple is not truly red in some objective sense. Its color is just a user-friendly icon your consciousness creates to signal high nutritional value. Hoffman supports this with a rigorous mathematical framework built from what he calls conscious agents. These are not necessarily human minds, but the most basic units of consciousness, defined by their capacity for experience and decision. In his model, these conscious agents interact with each other in vast, dynamic networks, and from their complex interactions, the entire world of space-time and physical objects emerges as a shared data structure. The physical world is the operating system that these conscious agents collectively generate and navigate. This provides a potential path to unify consciousness with physics, not by reducing mind to matter, but by deriving matter from mind. The theory is grounded in startling experimental evidence from perceptual psychology. Studies consistently show that our perceptions are not a direct video feed of reality, but a sophisticated construction. Our brain makes constant guesses, filling in blind spots, interpreting ambiguous data based on past experience. We see what is useful, not what is true. The famous hollow face illusion, where a concave mask appears as a normal convex face, demonstrates how our perception overrides raw sensory data with a powerful prior assumption about how faces should look. This is your brain's user interface in action, prioritizing fitness payoffs over factual accuracy. But does this finally solve the hard problem of consciousness? If consciousness is fundamental, then the question of how subjective experience arises from objective matter simply vanishes. There is no arising. Consciousness was always there, and matter is its creation. The deep mystery then shifts from why we are conscious to why this particular physical world, with its specific laws and constants, is the interface that a fundamental consciousness has chosen or been forced to project. It suggests that we are not biological machines that learn to feel, but timeless conscious agents that learn to build a biological machine to navigate a shared virtual reality. The search for a unified reality then leads us to a theory that seeks to weave all of existence into a single, geometric object. David Bohm saw a universe fractured by its own description. He believed our perception of separate objects in space and time was a profound illusion, a surface-level reality he called the explicate order. Beneath this visible world, Bohm proposed a deeper, hidden dimension, the implicate order, where everything in the cosmos is seamlessly and holistically enfolded into a unified whole. His theory grew from a deep unease with the standard Copenhagen interpretation of quantum mechanics. Bohm could not accept that reality was inherently fuzzy or that particles did not have definite properties until observed. He sought a more intuitive, objective foundation for the quantum world, one that restored a sense of concrete reality while still explaining its bizarre behavior. His solution was to propose that particles are always real and have a definite position, but they are guided by a mysterious, non-local influence he called the quantum potential. This potential is a wave that pervades all of space, an active information field that guides the motion of particles based on the entire quantum system. This explains the famous double-slit experiment without resorting to magic. The particle goes through one specific slit, but the quantum potential, shaped by both slits, guides it to the correct point on the detector screen, creating the interference pattern. The entire setup influences the outcome not through spooky action but through this underlying information field. To visualize the implicate order, Bohm used the beautiful analogy of a hologram. In a standard photograph, each part corresponds to a specific part of the object being photographed. If you tear the photo, you lose that information. But in a hologram, something miraculous happens. Every single fragment of the holographic film contains the entire image, just at a lower resolution. The whole is enfolded into every part. Bohm argued that the universe operates on this same principle. Every electron, every galaxy, and every conscious thought is a unique unfolding from this fundamental enfolded reality. The separateness you see is a temporary expression of a deeper, unbroken wholeness. This provides an elegant framework for understanding quantum non-locality, the eerie connection between entangled particles. If two particles are created together, their information becomes enfolded into the same region of the implicate order. Even when they are separated by vast distances, they are not truly separate at this deeper level. They remain a single, undivided entity. When a measurement is made on one, the entire system unfolds in a correlated way, instantly updating the state of its partner. There is no faster than light signal because there is no distance to cross in the implicate order, where all points are fundamentally one. The theory offers a compellingly intuitive picture, replacing the abstract mathematics of collapsing wave functions with a tangible, if hidden, process of unfolding and enfolding. Yet, it remains a minority view in physics. The primary criticism is that the quantum potential, while mathematically sound, introduces a level of non-locality so profound that it challenges our very conception of causality. Furthermore, the theory has not yet produced testable predictions that differ from standard quantum mechanics, leaving it in the realm of profound philosophical interpretation rather than falsifiable science. Does the implicate order truly describe the fabric of reality, or is it a beautiful metaphor for a truth we cannot yet grasp? It challenges us to see the universe not as a collection of things, but as a seamless, dynamic process of becoming, a cosmic hologram where each of us contains the whole. String theory's elegant vision of vibrating threads holds a secret, one that shatters the dream of a single, unique universe. The mathematics itself reveals not one solution, but a staggering multitude, a cosmic landscape of possible realities. This is the string theory landscape, a controversial but unavoidable consequence of the theory's own internal logic. The discovery came from probing the nature of the vacuum, the lowest possible energy state in a universe. In classical physics, a vacuum is simple emptiness, but in the quantum world, and especially in string theory, the vacuum is a complex tapestry of fields and forces. When physicists calculated the number of stable configurations these fields could settle into within the compactified extra dimensions, the result was breathtaking. They found not a handful, but an estimated 10 to the power of 500 distinct vacuum states. Each one of these stable configurations corresponds to a self-consistent universe with its own unique set of physical laws, its own values for the constants of nature. Imagine a vast, rolling terrain with 10 to the 500 distinct valleys. Each valley represents one possible vacuum state, one possible universe. Our cosmos is not special, it is simply one valley among an inconceivable number, a single garden in a wilderness of cosmic possibilities. This landscape provides a powerful, if contentious, answer to the riddle of fine-tuning. Why does our universe have just the right strength of gravity and the perfect mass for the electron to allow for stars, planets, and life? In the landscape view, there is no deeper reason. We simply find ourselves in one of the exceedingly rare valleys where the local laws are compatible with our existence. This is anthropic reasoning on a colossal scale. We could not possibly observe a universe where the constants forbid atoms or chemistry, so our very presence acts as a filter, selecting our specific cosmic address from an infinite array of uninhabitable worlds. This idea has ignited a firestorm of debate within theoretical physics. For some, the landscape represents a catastrophic failure of string theory's original promise. The goal was a unique theory of everything, one elegant equation that would predict all the forces and particles we see. Instead, we get a near-infinite menu of options, a theory that can seemingly predict anything and therefore explains nothing specific about our world. Critics argue it has moved from a testable scientific framework into the realm of untestable metaphysics. How can we ever verify the existence of universes we can never interact with? Proponents, however, see it as a profound and necessary step forward. They argue that expecting one unique universe from fundamental theory was always a form of hubris. The landscape, they claim, is a feature, not a bug, revealing a reality far richer and more democratic than we imagined. It suggests that the question why these laws is as meaningless as asking why Earth orbits the Sun. It is simply our local condition within a much vaster cosmic ecology. The debate cuts to the very heart of the scientific method, forcing us to ask whether a theory that describes a multiverse of unobservable realms can ever be considered science, or if it is the ultimate glimpse into the true, pluralistic nature of all that is. Our own cosmic home, with all its galaxies and stars, could be the interior of a black hole in a far larger universe. This is the breathtaking premise of black hole cosmology, a theory that turns the cosmos inside out. It suggests that the Big Bang was not the absolute beginning, but the violent formation of our universe from a singularity within a supermassive black hole belonging to a parent cosmos. This radical idea offers elegant solutions to some of our most persistent cosmic puzzles. One of the greatest is the mystery of the universe's low entropy. Entropy is a measure of disorder, and the early universe was in a state of astonishingly low entropy, incredibly smooth and ordered. This is like finding a room that has somehow tidied itself, a configuration so unlikely it demands an explanation. If our universe was born from the ultra-high entropy chaos of a collapsing star in a parent universe, how did it become so ordered? The answer lies in the transformative nature of the black hole collapse itself. The process of a star collapsing into a black hole may reset the entropy counter, scrubbing the slate clean and creating a new, low-entropy region on the other side of the singularity, which becomes a new Big Bang. Physicist Nikodem Poplawski has developed this theory using a specific version of Einstein's general relativity that incorporates particle spin. In his model, the intense torsion or twisting of spacetime at the moment of gravitational collapse could have prevented a true singularity from forming. Instead, the collapsing matter would rebound, erupting outward as the expanding universe we observe today. This provides a graceful bridge between the cosmic scale of general relativity and the quantum world, suggesting that the birth of our universe was a natural, physical process rather than a supernatural event. This theory also reframes the nature of dark energy, the mysterious force accelerating the expansion of our cosmos. In the black hole cosmology view, dark energy could be a subtle gravitational influence from the parent universe, gently pulling on the fabric of our spacetime from the outside. The ultimate fate of our universe is also transformed under this model. Instead of fading into eternal cold and darkness, the collapse of our own universe could seed the birth of new baby universes within its own black holes. Every black hole in our sky could be a portal to a new cosmos, a branch in an infinite fractal tree of reality. This creates a stunning vision of a multiverse not of parallel worlds but of nested ones, each with its own physical laws slightly altered in the birthing process. Could we ever find evidence for such a profound connection? Some scientists propose looking for a signature in the cosmic microwave background, the afterglow of our Big Bang. A specific pattern of polarization or a strange alignment of temperatures across the sky could be a fossil imprint, a whisper of the geometry of our cosmic parent. Others suggest that the overall shape of our universe might hold a clue. If we live inside a black hole, the geometry of space might carry a specific, detectable curvature imprinted by its origin. While the evidence remains elusive, the theory offers a majestic and humbling perspective, placing us not in a lone creation, but as one link in an endless, self-generating chain of cosmic life and death. This cosmic nesting doll of black holes suggests that information is not just stored at the boundaries, but that it might be the very source code of reality. The holographic anthropic multiverse weaves together three of our most profound theories into a single, breathtaking tapestry. It proposes that our universe is one of many holographic projections, its laws finely tuned for life because our conscious observation helps select it from an infinite menu of mathematical possibilities. Physicist James Gates made a discovery that sends a shiver down the spine of anyone who understands its implication. While working with the equations of supersymmetry, a theoretical framework that pairs every known particle with a superpartner, he found something utterly unexpected embedded within the math. The equations contained structures that were identical to error-correcting codes, the very same digital codes that ensure the integrity of data on your DVD or in a satellite transmission. It was as if he had peeled back the skin of reality and found lines of computer code staring back at him. These were not approximations or metaphors. They were exact, operational error-correcting codes woven into the fundamental laws that govern the universe. This suggests that the holographic principle is more than an analogy. It is a literal description of our cosmos. The three-dimensional world we experience, with its galaxies, planets, and people, could be a projection from a two-dimensional surface where information is stored in bits, complete with built-in error correction to maintain the stability of reality. How does this connect to the multiverse and the anthropic principle? Imagine an infinite library where every book contains the complete description of a possible universe, each with different physical laws. Most of these books describe barren, lifeless realities. The holographic anthropic principle suggests that our act of observation is like pulling one of these books off the shelf. Our consciousness does not create the universe, but it does select one specific, stable holographic projection from the vast ensemble of mathematical possibilities. We exist in this particular universe because its underlying code is stable enough and complex enough to support self-aware observers who can look back and see the code. The fine-tuning of the cosmos is not a miracle, it is a selection effect. We could not find ourselves in a universe whose code was too error-prone to form atoms or stars. The error-correcting codes found by Gates are the cosmic safeguards that make our specific, life-friendly reality a stable and consistent projection. This points to a truth far deeper than matter or energy. Information and computation appear to be the fundamental bedrock of everything. The universe is not just like a computer, it is a computer processing the mathematical rules that define its own existence. The solidity of your hand, the warmth of the sun, the vastness of space, all of it may be the output of a cosmic computation running on a two-dimensional screen at the edge of everything. Are we living in a universe that is, at its heart, a perfect and immutable mathematical truth? The future may be reaching back to shape the present. Time-symmetric quantum mechanics presents a universe where the flow of time is not a one-way street but a two-way dialogue. Developed by physicist Yakir Aharonov and his colleagues, this interpretation suggests that the present moment is not solely determined by the past. Instead, it is a product of both past and future boundary conditions, a handshake between what was and what will be. To describe a quantum system, Aharonov introduced the concept of a two-state vector. This is not a single description of a particle state, but a combination of two, one propagating forward from its preparation in the past and another propagating backward from its final measurement in the future. The reality we observe is the unique intersection where these two waves meet and agree. This is not mere philosophy. It is a framework that makes testable predictions through a technique called weak measurement. Unlike a standard quantum measurement that violently collapses a system into a single state, a weak measurement gently probes it, extracting just a tiny amount of information without fully disturbing its delicate quantum nature. By performing many of these gentle probes on an ensemble of particles, scientists can map out astonishing phenomena. They can observe a particle's average path through a double-slit apparatus, revealing that it seems to know where it will end up, its trajectory subtly guided by its final destination. This is the future in a very real sense, influencing the present. The implications for causality are profound. Our everyday intuition insists that causes must always precede their effects. But in this time-symmetric view, the future measurement is just as much a cause of the particle's behavior as its initial preparation. The universe appears to be a self-consistent whole, where the entire timeline is woven together in a way that makes the distinction between cause and effect blur into irrelevance. This immediately raises a deeply personal question. If the future can reach back and nudge the present, what does that mean for our own free will? Are our choices truly our own, or are they simply the inevitable fulfillment of a story whose ending is already written, reaching back to guide us toward it? Proponents of the theory offer a nuanced perspective. They suggest that free will might operate within this self-consistent framework. Your choices are genuine, but they are made in concert with the entire timeline of your life, a timeline that includes the consequences of those very choices. You are not a puppet on a string, but a co-author of a story that is being written from both the beginning and the end simultaneously. The universe, in this view, is not a chain of dominoes falling in a line. It is a cosmic symphony where every note is played in harmony with the final chord. A perfect, timeless composition where the future is not a blank page, but an active participant in the music of the present. The universe might be a cosmic grid, a vast checkerboard of cells flickering between simple states according to an eternal, unbreakable rulebook. This is the cellular automaton universe, a hypothesis that takes the idea of a digital physics and gives it a specific, breathtaking form. Pioneered by Stephen Wolfram, this theory suggests that the rich complexity of our physical world, from the swirl of galaxies to the double helix of DNA, emerges not from a set of profound equations, but from the relentless, step-by-step application of incredibly simple computational rules. The most famous example of this is Conway's game of life, a digital universe running on a simple grid. Each cell can only be on or off, alive or dead. The rules are basic, dictating that a live cell with too few neighbors dies of loneliness, while one with too many dies of overcrowding. From these three simple rules, an astonishing menagerie of complex behaviors emerges: gliders that sail across the grid, pulsars that blink on and off, and even self-replicating patterns. Our universe, Wolfram argues, could be a vastly more sophisticated version of this very game, running on a fundamental lattice of space-time itself. The laws of physics we have painstakingly discovered, like gravity and electromagnetism, would not be fundamental truths but large-scale statistical patterns, emergent phenomena that arise from the collective behavior of countless tiny computational cells updating their state. This shift in perspective is profound. It means that an electron is not a tiny billiard ball, but a stable, propagating pattern in the cellular automaton, much like a glider in the game of life. The collision of two particles is simply the interaction of two such patterns, governed by the underlying code. Evidence for this computational nature might be hidden in plain sight, woven into the patterns of nature. Look at a snowflake. Its intricate branching structure is not random. It is the result of simple growth rules playing out in a hexagonal lattice as water freezes. The spiral arms of a galaxy, the turbulent flow of a river, the branching of a tree, all of these could be the visible output of nature's hidden algorithms. Even the apparent randomness of quantum mechanics could be the result of underlying computational processes that are deterministic but so complex that they appear random to us. Just as the game of life is completely deterministic, yet produces unpredictable, complex results. This raises immediate and personal questions. If the universe is a deterministic cellular automaton, where does that leave our free will? Are our thoughts and choices just the inevitable output of a cosmic program that was set in motion eons ago? Proponents suggest that our consciousness could be a sophisticated pattern running on the automaton, a pattern so complex and self-referential that it experiences genuine agency. Your decision to lift your hand is a real computation happening within the universal computer, not a pre-recorded script. You are not a puppet, you are a complex subroutine with a degree of autonomy. This leads to the most tantalizing possibility of all. If our universe is computational, could we one day learn to read or even modify its source code? Understanding the fundamental rule set could give humanity a godlike ability to manipulate reality at its most basic level, healing diseases by rewriting cellular patterns or engineering new forms of matter by reprogramming the lattice. It would be the ultimate scientific achievement, moving from being users of the universe to becoming programmers of reality itself. The search for this cosmic code is a quest to see if the universe, in its heart, is not a chaotic explosion, but an elegant and profound computation. Our world is not the one true reality, but merely one neighborhood in a vast and infinite cosmos of equally real worlds. This is the startling claim of David Lewis' modal realism, a philosophical theory that takes the concept of parallel universes to its most radical and literal extreme. For Lewis, these are not just abstract possibilities or mathematical structures. Every conceivable world is a concrete, physical universe, as real and tangible as our own, isolated from us in a dimension beyond space and time. There is a world where you are the ruler of a global empire, a world where the laws of physics permit magic, and a world where dinosaurs never went extinct. In Lewis' view, none of these are mere fantasies. They are actual places with their own histories, their own stars and planets, and their own versions of you living out every possible life. Lewis introduced this idea to solve some of the most stubborn problems in metaphysics, logic, and language. We often talk about what is possible or necessary. We say it is possible for a horse to have wings, and it is necessary that 2 + 2 = 4. But what do these statements actually mean? Lewis argued that to say something is possible simply means that it is true in at least one of these real, concrete worlds. A winged horse does not exist here, but it gallops through the skies of another universe. To say something is necessary means it is true in all possible worlds. The logical truth of mathematics holds everywhere across the multiverse. This framework provides a beautifully clear and unambiguous foundation for reasoning about possibility and necessity, cutting through centuries of philosophical confusion. Yet, this elegant solution comes at a tremendous intuitive cost. It forces us to accept that an infinite number of grotesque, glorious, and utterly alien universes are just as real as the one we are experiencing right now. This violates our most basic feeling that our world is the primary, the actual one. Critics have relentlessly attacked this aspect, calling it an outrageous violation of Occam's razor. Why believe in such an extravagant multitude of worlds when we can explain possibility in a less extravagant way, perhaps as abstract ideas or mental constructs? Lewis' response was pragmatic. He argued that his system of modal realism, for all its seeming extravagance, provides the most systematic and useful framework for philosophy, semantics, and even science. It allows us to define concepts with perfect precision and understand the nature of truth and meaning in a way that other theories cannot match. The debate forces a profound choice. Do we cling to our intuition that this world is uniquely actual, even if it leads to philosophical dead ends? Or do we follow the logic where it leads, accepting a reality of infinite actualities, where our lives are just one thread in a tapestry of unimaginable scope? This is not just a game for philosophers. It challenges the very core of what we mean when we point to something and call it real. The universe is not a collection of static objects, but a flowing river of becoming. Alfred North Whitehead's process philosophy turns our conventional view of reality inside out, proposing that the fundamental ingredients of existence are not enduring substances, but fleeting events and dynamic processes. In this view, a rock is not a solid, permanent thing, but a slow-moving society of vibrating atoms, each itself a pattern of energetic activity. What we perceive as stability is merely a rhythm of change so slow and steady that it appears permanent to our senses. This directly challenges the substance metaphysics that has underpinned Western thought since Aristotle, which holds that reality is made of independent objects that merely have changing properties. Whitehead argued the opposite, that change is primary, and what we call objects are merely temporary stabilities in an endless flux of creative becoming. Your own sense of self is not a fixed entity, but a continuous process of experience, a thread of moments weaving itself into a coherent story. This perspective finds a powerful echo in modern physics. Einstein's theory of relativity fused space and time into a single dynamic entity, space-time, which curves and warps in response to mass and energy. It is a theory of relationships and processes, not of isolated things. A planet does not simply sit in space. It engages in an endless dance with the sun, its orbit a process defined by the geometry of the cosmic stage. Similarly, quantum mechanics reveals a world where particles have no definite identity or location until they enter into a relationship with something else. An electron is not a tiny ball, but a cloud of potential, a set of probabilities that only resolve through interaction. Its very nature is relational and process-driven. This process view offers a graceful escape from the ancient problem of mind-body dualism, the puzzle of how a non-physical mind can interact with a physical brain. If reality is fundamentally process, then mind and matter are not two different substances. They are different patterns or complexities of the same basic activity. A thought is not a ghost in the machine. It is the most sophisticated and intimate process that the brain, itself a complex process, enacts. Consciousness is not a thing that the brain produces. It is what the brain does at its highest level of organization. This provides a truly integrated view of reality, where everything from a fleeting thought to a spinning galaxy is part of a single, interconnected web of becoming. We are not separate beings in a universe of things, but interwoven events in a cosmic unfolding, each moment a new creation contributing to the ongoing life of the whole. A radical new framework is quietly rewriting the rules of physics, not by asking what happens, but by asking what can be done. This is constructor theory, proposed by physicist Chiara Marletto, and it represents a fundamental shift in perspective. For centuries, physics has been dominated by the language of initial conditions and dynamical laws, equations that tell us how a system evolves from one state to another over time. Constructor theory turns this on its head. It says the most fundamental statements in physics are not about what happens, but about what transformations are possible, and just as importantly, which ones are impossible. It focuses on the tasks that can, in principle, be performed. In this view, the laws of physics are not the differential equations of motion, but a set of very high-level principles about which physical transformations are possible and which are not. For example, the law of conservation of energy is not merely a formula. It is a fundamental statement that a machine which creates energy from nothing is an impossible task. A perpetual motion machine is not just impractical, it is forbidden by the deepest fabric of reality. This might sound like a simple rewording, but its implications are profound. It provides a unified language that can encompass quantum mechanics, thermodynamics, and information theory under one roof. Think of information. In traditional physics, information is a somewhat ghostly concept. But in constructor theory, information is physical and its properties are defined by what can and cannot be done to it. The fact that information can be copied but not created from nothing becomes a fundamental principle on par with the conservation of energy. This framework elegantly explains why some information is forever lost inside a black hole, not as a dynamical mystery, but as a statement of an impossible task. Recovering it is a transformation that reality simply does not permit. Constructor theory also offers a fresh path through some of quantum theory's thorniest puzzles. The bizarre phenomenon of quantum superposition, where a particle exists in multiple states at once, can be reframed as a statement about possible and impossible tasks. A particle in superposition is one for which a measurement that determines its state without disturbing it is an impossible transformation. The theory's power lies in its ability to distinguish between what is merely impractical with our current technology and what is fundamentally, physically impossible. This could finally provide a rigorous foundation for the physics of information, life, and knowledge itself, describing the universe not as a clockwork mechanism, but as an open-ended set of possible constructions, limited only by a few powerful and immutable laws of the impossible. Space itself may be a collective hallucination, a structure that arises from something far more basic. The emergent spacetime hypothesis proposes that the very stage of the universe, the three dimensions of space and one of time we navigate every day, is not a fundamental backdrop. Instead, it is a secondary, approximate reality that condenses out of a deeper, non-spatial quantum reality. This idea has gained immense traction from two major frontiers of theoretical physics. The first is loop quantum gravity, which attempts to describe the quantum nature of gravity without resorting to strings. It proposes that space is not smooth and continuous, but is woven from a fabric of tiny, finite loops, a network of discrete threads of gravitational field. On this incredibly minute scale, the familiar concept of space dissolves into a frothing quantum foam. The other key insight comes from the anti-de Sitter/conformal field theory correspondence, often called the AD-S/CFT correspondence. This is a powerful, if abstract, mathematical duality. It shows that a theory of gravity operating in a hypothetical warped space can be perfectly equivalent to a quantum field theory that lives on that space's lower dimensional boundary, a theory that has no gravity in it at all. This is a concrete realization of the holographic principle, where a higher dimensional spacetime, complete with gravity, emerges holographically from a lower dimensional quantum system that knows nothing of gravity or conventional space. But if spacetime is not fundamental, what is it made of? What are the building blocks from which it crystallizes? One of the most compelling proposals is quantum entanglement. Entanglement, that spooky connection between distant particles, might be the very glue that stitches space together. Think of space not as a container, but as a web of correlations. Every time two quantum systems become entangled, it is as if a new thread is spun between them. The more entanglement, the stronger the connection, and the shorter the emergent distance in space. If you were to somehow sever all the quantum entanglement between two regions, the space between them would literally tear apart. Another possibility is that spacetime emerges from pure information processing, from the computational activity of fundamental bits, much like the world of a video game emerges from the calculations of its processor. Or it could emerge from a causal set, a collection of discrete events with only a bare notion of which event causes another, without any preconceived idea of distance or duration. From this sparse, minimalist network of cause and effect, the full richness of a four-dimensional spacetime could potentially be reconstructed. The implications of this are almost beyond comprehension. If spacetime is emergent, then the Big Bang was not an explosion in space. but the moment when space and time themselves first precipitated into existence from a more primitive state. The smooth geometry described by Einstein might be a kind of thermodynamic average, a large-scale approximation, much like the smooth surface of a lake emerges from the frantic motion of countless water molecules. This suggests that under extreme conditions, like at the center of a black hole, space and time could lose all meaning, dissolving back into their constituent parts. The flow of time, that most persistent of illusions, might be a consequence of the universe moving towards higher states of complexity or entanglement. We are not living in a universe within space-time, but are instead embedded within a universe that is constantly weaving the very fabric of space-time into being, moment by moment, from a hidden quantum tapestry we are only beginning to perceive. Space may not be a fundamental stage, but a crystal that slowly formed as the universe cooled. The quantum gravity model proposes exactly this, suggesting that the empty void is actually a dynamic web of relationships, a graph of countless points connected by links. In the fiery first moments of the cosmos, this graph was a blazing chaos, a complete graph where every single point was connected to every other point. There was no sense of distance or direction, no here or there, just a featureless, high-energy blur. Then, as the universe expanded and cooled, this network underwent a cosmic phase transition, much like steam condensing into water or water freezing into ice. The vast majority of those primordial connections froze and shattered, leaving behind a sparse, stable lattice that defines the structure of our reality. This emergent lattice is what we now experience as the three dimensions of space and one of time. The reason we live in a four-dimensional world is not a divine mandate, but a statistical accident, the most stable configuration that this cosmic graph could settle into as it lost its initial heat. This framework beautifully bridges the worlds of condensed matter physics and quantum gravity. We know from everyday life that when a material like water freezes, its properties change dramatically because of the new, orderly arrangement of its molecules. Quantum gravity applies this same logic to spacetime itself, treating the vacuum as a kind of cosmic material undergoing a phase change. The model also offers an elegant explanation for one of the most precise symmetries in nature, Lorentz invariance, the principle that the laws of physics are the same for all observers moving at constant velocity. In this view, Lorentz invariance is not a fundamental law, but an emergent property, an accidental symmetry that arises because the underlying graph looks the same in all directions from our low-energy, large-scale perspective. Just as a crystal lattice looks smooth and continuous from a distance, so too does the graph of spacetime appear to us as a smooth, symmetrical continuum. Could we ever find evidence for this pixelated origin of space, the theory makes a fascinating prediction. If spacetime is a discrete graph, then very high-energy particles like cosmic rays might be able to sense its graininess. A photon traveling across billions of light-years might be subtly scattered by the microscopic structure of the graph, much like light is scattered by the molecules in the air, creating a faint haze in the distant universe. Our most powerful telescopes are now searching for this exact signal, a blurring of the most distant gamma-ray bursts that could be the first experimental hint that space is not smooth, but built from a web of frozen relationships. This represents a truly viable path to a theory of quantum gravity, as it does not attempt to quantize gravity itself, but instead shows how gravity and spacetime could naturally emerge from a more basic, non-geometric reality. We are not living in a universe of smooth curves, but on the stable surface of a cosmic ice flow, a structure that formed in the great freeze of creation. The smooth fabric of spacetime might be a grand statistical mirage. Causal set theory offers a radically minimalist vision, proposing that reality is built not from a continuous geometry, but from a vast collection of discrete events like grains of sand, connected only by a fundamental sense of cause and effect. This approach, championed by physicists like Raphael Sorkin, seeks to unify general relativity and quantum mechanics by taking their core insights to a new extreme. From relativity, it borrows the primacy of causality, the unbreakable rule that causes must always precede their effects. From quantum theory, it adopts the idea of discreteness, that nature is ultimately granular, not smooth. A causal set is the ultimate simplification of this union, a sprawling network of individual points where the only defining property is which events can influence which others. There are no pre-existing notions of distance or duration, no background stage. Space and time as we know them are not fundamental ingredients. They are collective phenomena that emerge from the sheer number of these causal relationships. Think of a sprawling family tree. The tree itself has no physical size, yet it contains a rich structure of relationships of who descended from whom. From the intricate pattern of these genealogical links, you can infer a great deal about the passage of time and the separation between branches. Our four-dimensional spacetime continuum is like that family tree viewed from a great distance, its discrete points blending into a smooth, continuous history. This perspective provides a potential solution to one of the most vexing problems in theoretical physics, the problem of time. In general relativity, time is dynamic and intertwined with space, but in standard quantum mechanics, time is an external, unchanging parameter. This conflict creates a deep inconsistency. In causal set theory, time is not a parameter at all. It is inherent in the very order of the events. The flow of time is literally the process of new events being added to the set, each new point forging its own unique web of causal links to the existing structure. The universe is not evolving in time, it is growing as time, crystallizing moment by moment. This growth is believed to be random, a probabilistic process that, over an immense number of steps, generates a structure that looks remarkably like our own cosmos at large scales. How could such a sparse set of points possibly recreate the rich, smooth geometry we experience every day? The answer lies in a concept called geometric randomness. Imagine you are looking at a finely detailed photograph from a newspaper. Up close, you see it is made of nothing but individual, discrete black and white dots. Yet, from a normal viewing distance, those dots blend seamlessly to form a continuous image of a face or a landscape. In the same way, the causal set is the underlying dot matrix of reality, and our perception of a smooth continuum is an illusion of scale, a consequence of our macroscopic viewpoint. For this to work, the causal set must be incredibly dense, containing a staggering number of elements, far more than the number of atoms in the observable universe. This immense density is what washes out the graininess, creating the smooth appearance of spacetime. The theory remains highly theoretical, a compelling blueprint that has yet to make concrete, testable predictions. But its profound simplicity is its greatest strength, stripping reality down to its most essential components, causality and discreteness, and asking if the entire cosmic edifice can be rebuilt from there. It suggests that the stage of our existence is not a given, but a magnificent and unexpected consequence of a deeper, more causal order. The smooth geometry of Einstein's universe shatters into a billion tiny loops. Loop quantum gravity presents a vision of reality where space itself is not a continuous backdrop, but a fabric woven from individual, discrete threads of gravitational field. This is a background-independent theory, meaning it does not treat space and time as a pre-existing stage on which matter performs. Instead, space and the relationships within it are the entire show, emerging from a deeper, more fundamental network. Pioneered by physicists like Abhay Ashtekar, Lee Smolin, and Carlo Rovelli, this framework emerged as a direct and radical alternative to string theory. While string theory attempts to unify all forces by adding extra dimensions and vibrating strings, loop quantum gravity takes Einstein's general relativity at its word and seeks to quantize the fabric of spacetime itself. It asks a simple, profound question: what if gravity is geometry and geometry is made of quantum parts? The answer lies in a mesmerizing structure known as a spin network. Imagine the cosmos as a vast, evolving web of connections. Each line in this web represents a fundamental thread of space carrying a tiny, quantized unit of area. The points where these lines intersect are where the fabric of reality is woven together. These spin networks are not embedded in space, they are space. Their connections define proximity, and their evolution defines the passage of time. This leads to the theory's most concrete prediction, the granularity of space. Just as a digital photograph dissolves into pixels when you zoom in, space-time itself has a fundamental resolution. There is a smallest possible area and a smallest possible volume measured in tiny Planck units. You cannot have half a unit of space any more than you can have half a pixel on your screen. This discrete structure provides an elegant escape from the terrifying infinities that plague classical physics, the singularities at the heart of black holes and the moment of the Big Bang. In Einstein's theory, these are points of infinite density where the laws of physics break down. But in the loop quantum gravity picture, the weave of spacetime is so fine that it cannot be compressed to an infinite point. The collapse of a star into a black hole would reach a maximum density and then rebound, perhaps erupting as a new universe. The Big Bang was not a singular beginning from nothing, but a great bounce from a previous cosmic phase. The universe did not appear in a single flash but transformed. Does this mean we could see echoes of a universe that existed before our own? Some models suggest that the patterns in the cosmic microwave background, the oldest light we can observe, might hold faint imprints from that pre-bounce era, a cosmic fossil from a time before time. Yet for all its conceptual beauty, loop quantum gravity faces immense challenges. The theory has brilliantly quantized space, but the quantization of time remains deeply puzzling. Furthermore, while it describes the quantum states of space, connecting this abstract spin network back to the smooth, classical world we experience every day has proven extraordinarily difficult. How do we get from a shimmering quantum weave to the definite chair you are sitting on? The theory also struggles to incorporate the other fundamental forces, like electromagnetism and the nuclear forces, in a complete and unified way. It provides a compelling quantum picture of gravity and space, but whether it is the final, complete picture of quantum spacetime is a question that continues to drive research at the very frontier of theoretical physics. It offers a universe built from relationship and connection, a cosmic tapestry where every thread is a finite quantum of reality itself. The smooth geometry of spacetime might be nothing but a fleeting shadow. A new way of calculating the outcomes of particle collisions is revealing a reality far stranger, a geometric shape known as the amplituhedron. This discovery is quietly dismantling two of the most sacred pillars of modern physics, locality and unitarity. Locality is the simple idea that objects can only interact if they are close together, and unitarity is the principle that probabilities in any quantum interaction must always add up to 100%. These concepts are the bedrock of our current theories, but the amplituhedron suggests they are not fundamental. They are themselves emergent properties, side effects of a deeper, more perfect geometric truth. The work of physicist Nima Arkani-Hamed and his collaborators led to this stunning breakthrough. They were wrestling with the mind-numbing complexity of calculating scattering amplitudes, the probabilities of what happens when particles like electrons and photons collide. These calculations, essential for our understanding of particle physics, were so convoluted that they often required thousands of pages of intricate algebra, with countless terms cancelling each other out in seemingly miraculous ways. Arkani-Hamed asked a radical question: what if all that exhausting algebra was just a clumsy way of describing something much simpler, a pristine geometric object? The amplituhedron is that object. It is a multifaceted jewel living in an abstract space, and its volume directly gives the probability of a particle collision. In this new picture, you do not need to painstakingly track every possible force-carrying particle and every interaction through space and time. You simply calculate the volume of the amplituhedron, and the answer for how particles will scatter emerges with breathtaking elegance and simplicity. The implications are profound. In our standard view, particles interact by exchanging other particles in a specific location, a process that respects locality and unfolds in a unitary way. But the amplituhedron calculation shows no trace of these principles. It does not mention particles moving through space or forces being exchanged. Locality and unitarity simply fall out of the geometry. They are consequences, not causes. This suggests that spacetime itself, the arena where these local interactions appear to happen, is not the fundamental foundation of reality. Instead, spacetime and the quantum rules that govern it might both be emergent phenomena, projections from a more fundamental, non-spatial geometric realm. The amplituhedron exists in a Platonic landscape of perfect forms, and our universe of forces, particles, and dimensions is merely a shadow it casts. This points toward a universe where the deepest truths are not stories of cause and effect in time, but timeless, immutable mathematical beauties. We are left to wonder if the solid world we inhabit is just a clumsy translation of a magnificent, silent geometry. Two threads of reality, seemingly unrelated, may be the same cosmic fabric seen from opposite sides. The ER equals EPR conjecture proposes a breathtaking equivalence between the spooky connection of quantum entanglement and the cosmic shortcuts of wormholes. Quantum entanglement, famously described by Einstein, Podolsky, and Rosen as spooky action at a distance, links particles so that measuring one instantly influences its partner, no matter how far apart they are. General relativity, on the other hand, describes wormholes or Einstein-Rosen bridges as tunnels through space-time connecting distant locations. For decades, these were considered completely separate phenomena, one belonging to the quantum world and the other to the geometry of gravity. Physicists Juan Maldacena and Leonard Susskind made the radical suggestion that they are, in fact, two different descriptions of the same underlying reality. An entangled pair of particles is not just correlated, it is subtly connected by a microscopic wormhole. This is not a wormhole you could travel through. It is a ghostly, non-traversable bridge, but its geometric existence is what creates the instantaneous quantum link. This idea provides a stunningly elegant bridge between the two great pillars of modern physics. Quantum mechanics and general relativity have been at odds for a century, each ruling its own domain but refusing to be united. The ER equals EPR conjecture suggests that the key to their union has been hiding in plain sight, written in the language of quantum information and spacetime geometry. The implications rewrite our understanding of reality itself. It suggests that spacetime, the very stage of the universe, might be built from a vast, intricate network of quantum entanglement. Think of the fabric of space as a cosmic tapestry. Each thread in that tapestry is a quantum entanglement between 2 points. Weave enough of these threads together, and the smooth, continuous illusion of space emerges. Where entanglement is dense, space is strongly connected. Where there is no entanglement, space literally falls apart. This provides a profound new perspective on the holographic principle. The information that describes a volume of space is encoded on its boundary, and that encoding is accomplished through the specific pattern of entanglement between the boundary points. A wormhole, then, is simply the geometric manifestation of a maximally entangled state. This transforms our view of black holes. The event horizon of a black hole is not a terrifying cliff of no return, but a highly entangled surface. The information that falls into a black hole does not vanish. It becomes scrambled into the quantum connections that form the wormhole, linking the black hole to another part of the universe, or perhaps to another universe entirely. The firewall paradox, a major crisis in theoretical physics concerning what happens at the heart of a black hole. may be resolved by this elegant duality. The violent quantum drama is tamed into a smooth geometric passage. Could this be the fundamental clue to a complete theory of quantum gravity? It suggests that gravity is not a fundamental force, but an emergent phenomenon, a consequence of the universe's quantum information trying to stay connected. We are not living in a universe with space and particles, but in a universe that is, at its heart, a dynamic web of quantum relationships, whose intricate weave casts the shadow we perceive as geometry, force, and matter. The solid ground beneath your feet and the vast emptiness between stars are both illusions, emergent from a deeper, connected whole where everything is linked to every other thing by threads of information and geometry forever intertwined. This profound connection hinted at by ER equals EPR leads us to a foundational question. What is the nature of the information that weaves reality together? John Wheeler's It from Bit hypothesis offers a stunningly simple answer, proposing that every particle, every force field, and even the fabric of spacetime itself ultimately derives from immaterial bits of information. Wheeler, the same physicist who gave us the participatory anthropic principle, suggested we reverse our entire perspective. We traditionally assume that the physical world is primary and that information, like the data in a book, is just a secondary description of that world. The it from bit idea turns this on its head, asserting that the physical world, the it, emerges from the bits. Imagine the universe as an endless cosmic questionnaire. At the most fundamental level, reality is not made of stuff, but is constantly answering a ceaseless stream of binary yes-no questions. Does a particle exist here? Yes. Is it spin up? No. Each answer is a single bit, a definitive 1 or 0, and the colossal tapestry of these answers, accumulated over eons, constructs the illusion of a continuous physical reality. Your chair feels solid not because it is made of solid substance, but because an unimaginably dense network of information bits consistently returns the answer yes to the question of its existence and location. This is not the same as the simulation hypothesis, where a computer is running the code. In Wheeler's vision, the bits are not running on any physical hardware, they are the hardware. Information is the fundamental substance, the very bedrock of existence. This idea has found fertile ground in modern physics. The holographic principle, where a three-dimensional universe is encoded on a two-dimensional surface, is a direct mathematical realization of it from bit. The pixels of that cosmic screen are pure information. Similarly, the discovery of error-correcting codes in the equations of supersymmetry provides a tantalizing clue that the universe operates with the same logical integrity as a digital system, safeguarding its own data. But what does it mean for a bit to be fundamental? A bit is not a thing, it is a distinction, a choice between two alternatives. Wheeler was suggesting that existence itself arises from a primordial act of distinction. Before there is a here or a there, a now or a then, there is a single, fundamental question being posed, and the first yes gives birth to space, while the first no carves out a boundary. This transforms our understanding of what is real. Matter and energy are no longer the primary actors. They are complex, stable patterns of information, much like an intricate novel emerges from the simple arrangement of 26 letters. The laws of physics are not the rules of a mechanical universe, but the consistent statistical habits of how these cosmic bits tend to answer their questions. This leads to a deeply participatory view of reality, for a question implies a questioner. Who or what is posing the cosmic questionnaire? Wheeler believed that observers, through the very act of measurement and observation, are essential to bringing the universe into definite existence from a fog of potential. We are not just reading the cosmic bits, our interaction with the world is the process that elicits the answers, forcing the bits to commit to a 1 or a 0 and solidifying the reality we perceive. The it from bit hypothesis challenges us to see the cosmos not as a grand machine, but as the world's most profound and ongoing computation, a universe where information is not just what we learn about reality, it is what reality is made of. Yet this cosmic computation reveals a startling secret about time itself. The thermal time hypothesis proposes that time, as we feel it passing, is not a fundamental feature of the world, but a side effect of thermodynamics, a ghost born from the statistical tendency of the universe toward disorder. This radical idea, developed by mathematicians Elaine Connes and physicist Carlo Rovelli, suggests that the flow of time is an emergent property, a direct consequence of a system being in a state of thermodynamic imbalance. We do not inhabit a universe with a built-in clock. We are part of a process that creates the appearance of one. The theory begins with a deep puzzle in modern physics known as the problem of time. In Einstein's general relativity, time is dynamic and malleable, woven into the fabric of space-time. But when we try to apply the rules of quantum mechanics to the entire cosmos, time seems to vanish from the fundamental equations altogether. The most basic description of reality appears to be timeless, presenting a glaring contradiction with our most intimate experience of life. The thermal time hypothesis offers a way out. It posits that time is not a primary ingredient but a secondary statistical feature. In any complex quantum system, a special state, known as the thermal state, can be used to define a flow. This thermal flow is what we perceive as the passage of time. Essentially, time is the expression of the universe's inherent tendency to move from order to disorder, from low entropy to high entropy. This is the famous arrow of time, and according to this hypothesis, it is the very source of time's flow. Think of a cup of hot coffee cooling in a room. The heat flows from the coffee into the cooler air, and this irreversible process defines a clear direction from hot to cold, from order to disorder. Now, imagine that every single event in the universe, from the motion of planets to the firing of your neurons, is part of this grand cosmic process of heat dissipation and increasing entropy. The thermal time hypothesis suggests that our perception of time ticking forward is our internal experience of this universal, one-way slide toward equilibrium. This profoundly links our sense of time to the quantum world and the quest for a theory of quantum gravity. In a fundamental, pre-geometric reality, where there may be no space and time as we know them, what exists are quantum correlations and states. When one part of this quantum system is in a thermal state relative to another, it generates a clock. Time emerges from the quantum statistics of the system, much like temperature emerges from the average motion of molecules. You do not feel the jostling of individual air molecules, you feel a single sensation of warmth. In the same way, you do not perceive the fundamental, timeless quantum correlations. You perceive their collective, statistical behavior as the relentless flow of time. What does this mean for your own experience? Your conscious awareness, with its clear sequence of past, present, and future, would then be a direct reading of this thermodynamic gradient. Your brain is an incredibly complex, non-equilibrium system, constantly processing information and increasing entropy. The feeling that time is passing is the feeling of your own neural machinery operating far from thermal equilibrium, constantly updating its state as it interacts with a world that is also sliding toward disorder. This suggests that if the universe ever reached a state of maximum entropy, a hypothetical heat death where everything is in perfect balance, the flow of time would simply cease. There would be no before and no after, because there would be no processes left to define a direction. The clock would stop, not because it broke, but because the very concept of ticking would have lost all meaning. The thermal time hypothesis presents a cold, elegant, and deeply unsettling vision, one where the river of time is not a river at all, but the statistical shadow of a timeless quantum reality. A fragile quantum superposition cannot survive contact with the open air. The world of definite objects we take for granted emerges from a quantum shadowland through a relentless process of selection, a theory known as quantum Darwinism. Developed by physicist Wojciech, this framework tackles the deepest mystery of quantum theory, the measurement problem, by asking not why the quantum world is so weird, but why our classical world seems so stubbornly normal. Its answer lies not in a mysterious collapse, but in the mundane but powerful influence of the environment. Imagine a single quantum particle, like an electron, existing in a blurry superposition of two different states, spin up and spin down. This delicate state is incredibly fragile. The moment it interacts with its environment, with even a single photon of light or a stray air molecule, something profound happens. The quantum coherence, the delicate interference between the two possibilities, is destroyed. This process is called decoherence, and it happens almost instantaneously for any object large enough to see. But decoherence alone does not explain why we see one outcome and not the other. It explains why we do not see a cat that is both alive and dead, but it does not explain why we see a cat that is definitively alive. This is where quantum Darwinism makes its crucial contribution. Jacques proposed that while the environment destroys most quantum superpositions, it also acts as a broadcasting system, copying and disseminating information about the surviving states. When a quantum system interacts with its surroundings, certain states are robust. They leave a lasting imprint, while others are fragile and are wiped away. These robust states are called pointer states, and they are the ones we consistently observe in the classical world. The position of a chair is a pointer state. It is stable against environmental disruption. Its simultaneous existence in multiple positions is not. The environment does not just measure the system once, it measures it countless times, with every photon that bounces off it, every air molecule that collides with it. Each of these interactions creates a copy of the same information. The chair is here. Quantum Darwinism argues that what we perceive as objective reality is simply the consensus information that has been widely replicated and scattered throughout the environment. You see a definite table not because your brain collapses a wave function, but because the photons carrying the image of the table to your eyes are all telling you the same redundant story. They all agree on the table's location because that information has been redundantly imprinted on the environment by trillions upon trillions of prior interactions. Your observation is just the final step in a long chain of natural selection, where only the fittest, most stable quantum states survive to be copied and perceived. This provides an elegant explanation for why we all seem to share the same objective world. We are all simply accessing the same widely distributed, redundant information. Different observers can measure the same system and get the same result because they are all tapping into the countless environmental imprints that all say the same thing. The universe achieves objectivity through redundancy. Does this finally solve the measurement problem? For many physicists, quantum Darwinism provides the most compelling and physically grounded account of the quantum to classical transition we have. It replaces the magical, unexplained collapse with a dynamical process of environmental interaction and information copying. It bridges the gap between the probabilistic quantum realm and the definite classical world using the established principles of decoherence and information theory. Yet a deep mystery remains. The theory explains how a single, definite outcome is selected from the quantum soup, but it still takes the existence of multiple possible outcomes as a given. It describes the mechanism of selection beautifully, but the fundamental question of why there is a probability distribution in the first place, the origin of the quantum probabilities themselves, remains untouched. We are left with a universe that chooses its definite face through a constant, silent conversation with itself. A conversation whose initial rules we can describe but whose ultimate origin we still cannot fathom. A universe without true chance might seem impossible given the quantum world's famous randomness. Yet the superdeterminism interpretation dares to propose just that, arguing the quantum dice were never rolled at all. This controversial theory suggests that the apparent randomness and spooky connections we observe are not fundamental features of nature, but illusions born from a deeper, completely deterministic reality. According to superdeterminism, the hidden variables that dictate a particle's behavior are not independent of our decision to measure them. In fact, the correlations are set in stone from the very beginning of the universe. Your choice to measure a particle's spin in a specific direction was not a free choice at all, but a predetermined event perfectly correlated with the hidden state of the particle itself. This single, radical idea challenges the very foundation of how we interpret quantum experiments. The famous Bell's theorem, which seemed to slam the door on hidden variable theories, relied on a crucial assumption that the settings of our measuring devices are chosen independently of the hidden states of the particles we are studying. Superdeterminism boldly rejects this assumption of statistical independence. It proposes that the entire experimental setup, including the scientist's mind and the apparatus, shares a common causal past with the particle, weaving a web of pre-established harmony that makes the particles seem to communicate faster than light. Physicists like Nobel laureate Gerard T. Hooft have championed this view, developing models where the quantum world emerges from an underlying deterministic system, much like the pixelated world of a computer game emerges from deterministic bits. He argues that the chaotic complexity of this underlying layer creates the perfect illusion of probability and indeterminacy at our level of observation. The debates surrounding this idea are among the most heated in all of physics. Proponents see it as the most elegant escape from the paradoxes of quantum theory, a way to restore a classical, cause-and-effect universe without spooky action. For them, it is a viable solution that simply requires us to accept a more interconnected cosmic history. Critics, however, fire back with a deeply unsettling counterargument. If superdeterminism is correct, then our own sense of free will is a complete and utter illusion. Every experiment we design, every question we ask of nature, was predetermined at the dawn of time, locked in a cosmic script written by the initial conditions of the universe. This, they argue, makes science itself impossible, for how can we trust our experiments to reveal objective truths if our very methods of inquiry are pre-programmed to confirm what was always destined to be? The theory forces a profound choice. Do we accept a universe with genuine randomness and spooky connections to preserve our sense of free inquiry? Or do we embrace a clockwork cosmos of absolute determinism, where our every thought and action was written in the stars eons ago? Quantum properties are not absolute truths of the universe, but exist only in the eye of the beholder. This is the profound shift proposed by Carlo Rovelli's relational quantum mechanics. In this view, an electron does not have a definite spin, up or down, in and of itself. Its properties are defined purely through its interactions, its relationships with other systems. An electron has spin up relative to one measuring device, and at the very same time it could have spin down relative to another. There is no single God's eye view of what the electron really is. Reality is not a collection of things with intrinsic properties, but a vast network of relations. This elegantly dissolves the paradox of Schrödinger's cat. The cat is not both dead and alive in an absolute sense. For you, outside the box, the cat exists in a superposition of possibilities. But for a particle of air inside the box, the cat state is already a concrete fact. Both perspectives are equally valid and real, they are just relative to different systems. The universe does not force a single history. It contains a multitude of interlocking but partial descriptions, each true from its own point of view. This idea resonates deeply with Einstein's theory of relativity. Just as relativity taught us that there is no universal now, that simultaneity is relative to the observer's motion, relational quantum mechanics asserts that quantum states themselves are relative to the observer. There is no single objective quantum wave function for the entire universe. There are only countless individual wave functions, each describing a system from the perspective of another system that has interacted with it. You, your measuring device, and the electron are all physical systems on equal footing. When you measure the electron, you are not a magical consciousness collapsing a wave. You are one physical system interacting with another, and an outcome becomes definite relative to you. The spooky connection of quantum entanglement also loses its mystery. Two entangled particles are not communicating faster than light. They are simply sharing a common history. Their correlation was established when they interacted in the past, and now, for any observer who measures one, the state of the other becomes definite relative to that observer. Another observer who has not yet measured either particle would still describe them as entangled. This is not a contradiction. It is just a reflection of the different relationships each observer has with the quantum system. The world is not weird, it is relational. So where does this leave our search for an objective reality? It suggests that objectivity is not about a single, true description of the world, but about the consistency we find when we compare our individual relational accounts. We all agree a table is solid because our various interactions with it, from every possible angle, yield consistent, redundant results. The table is real because of the stability of its relationships with everything else. This makes reality a conversation, a cosmic network where things are defined not by what they are in isolation, but by how they connect and interact. Does this relational view finally provide the most coherent map of the quantum world, one where the paradoxes simply fade away, not because they are solved, but because the question of a single, absolute reality was always the wrong one to ask? Perhaps the quantum world's blurry potential simply cannot last forever. Objective collapse theories propose a startling alternative to the measurement problem, suggesting that wave functions do not require an observer to collapse. Instead, they break down spontaneously and inevitably, driven by a fundamental physical process woven into the fabric of reality itself. This is not a philosophical interpretation, but a proposed modification to the mathematical core of quantum mechanics. The Garadi-Rimini-Weber, or JRW, theory was one of the first concrete models. It introduces a simple but profound mechanism. Every particle has a tiny, fixed probability that at any given moment its wave function will spontaneously localize, abruptly ceasing to be spread out and snapping into a definite position in space. For a single particle, this spontaneous collapse is exceedingly rare, perhaps happening only once every 100 million years. But an object you can see, like a chair or a cat, is made of trillions upon trillions of particles. According to the JRW model, the wave function of the entire object is tied to the states of all its constituent particles. This means that the chance of at least one particle in the object undergoing a spontaneous collapse at any given moment becomes overwhelming. The entire system's wave function collapses almost instantly, ensuring that macroscopic objects are always in a definite state, never in a ghostly superposition. This elegantly explains why we never see a cat both alive and dead, while preserving the strange quantum behavior for tiny, isolated particles. Another powerful approach links this spontaneous collapse to the most familiar force in our lives, gravity. The Diosy-Penrose model, developed by physicists Lajos Diosy and Sir Roger Penrose, proposes that gravity itself is the trigger for wave function collapse. The theory suggests that a particle in a superposition of two different locations is in effect creating two slightly different gravitational fields. Maintaining this split in the fabric of spacetime requires energy. According to Penrose, this gravitational superposition is inherently unstable. After a very short time that depends on the mass and separation of the states, the system will spontaneously choose one configuration, collapsing the wave function to avoid the uncomfortable strain of bending spacetime in two different ways at once. For an electron, this collapse time would be astronomically long, but for an object with any significant mass, even a tiny dust grain, the collapse would be almost instantaneous. In this view, the definite reality of the macroscopic world emerges because gravity, the architect of cosmic structure, cannot tolerate quantum ambiguity on large scales. These are not just philosophical ideas, they are testable scientific theories that make predictions different from standard quantum mechanics. The spontaneous and random nature of the collapse in GRW would introduce a minuscule but potentially detectable noise into the motion of particles. Exquisitely sensitive experiments are now searching for this signature, monitoring tiny mirrors or floating nanoparticles cooled to near absolute zero, watching for an unexplained jitter that could be the whisper of a wave function collapsing on its own. The Diossi-Penrose model predicts a fundamental limit to the precision of certain experiments, a blurring imposed by nature itself that would become more pronounced for heavier objects. Researchers are designing new matter-wave interferometers, devices that measure the wave-like nature of increasingly large molecules, to see if this gravitational collapse effect begins to appear as mass increases. Do these objective collapse theories represent a necessary fix to quantum mechanics? They offer a starkly different vision of reality, one where the definite world we experience is not an illusion created by our minds or our environment, but a direct consequence of a new, fundamental law of nature. The transition from the quantum to the classical is not a mystery of observation, but a physical process as real as gravity. A quiet, continuous event happening all around us, ensuring the solidity of the world by constantly choosing what is real. The solidity of objects might be a distraction from the true architecture of reality. Category theory, an immensely abstract branch of mathematics, proposes that the fundamental essence of everything is not found in things themselves, but in the relationships and connections between them. While traditional mathematics often focuses on the internal properties of objects, like the numbers in a set, category theory zooms out. It studies the patterns of arrows, the transformations and processes that link different mathematical structures together. The power is in the map, not the territory. A single object is defined not by what it is, but by its relationships to everything else in its category. This perspective is so general that it can be applied to nearly anything, from the logic of computer programs to the very fabric of the cosmos. Physicists like John Baez have championed this approach as a potential path to a unified theory of physics. In his work, The Bizarre Rules of Quantum Mechanics and the Smooth Geometry of General Relativity are not seen as two separate sets of equations to be forced together. Instead, they are viewed as two different categories, and the quest for quantum gravity becomes the search for the higher-level functors, the mathematical translators that can map one category onto the other while preserving their essential relational structures. It is a search for the deep grammar that underlies all physical law. Could this be the ultimate language of reality? Our conventional physics is built on set theory, which treats the world as a collection of distinct objects with properties. But what if the universe is not a collection of things at all? Category theory suggests a reality where relationships are primary, and objects are merely the nodes where complex webs of interaction temporarily stabilize. The electron is not a tiny ball, but a nexus of interactions with other particles and fields. Space-time itself might not be a fundamental container, but a category that emerges from a more basic network of causal relations. This framework offers a stunningly elegant way to describe systems where wholeness and interconnection are paramount, from the entangled states of quantum particles to the intricate feedback loops of a living ecosystem. The promise is a mathematics that can finally describe a universe of process and becoming, rather than a static universe of being. We are left to wonder if the ultimate theory of everything will not be a single, monumental equation, but a timeless relational structure, a cosmic syntax where the meaning of every particle and every force is defined entirely by its place in the web of all connections. The relationships described by our equations might be more real than the things we think they describe. Structural realism is a powerful philosophical stance that argues the true content of our scientific theories is not the nature of fundamental entities, but the stable structure of relationships between them. It suggests that while our ideas about what an electron is have changed radically over the centuries, the mathematical web describing how electrons relate to photons, magnetic fields, and other particles has remained remarkably constant. This distinction gives rise to two nuanced versions of the idea. Epistemic structural realism is the more cautious approach, claiming that the structure is all we can ever know about the world. The things in themselves, the ultimate nature of quarks or spacetime, might forever lie beyond our grasp. We are like scientists studying a black box, only able to map the connections between its inputs and outputs without ever seeing the internal machinery. Ontic structural realism, however, makes a far bolder claim that the structure is all there is. There are no hidden objects or self-subsisting entities, only a vast dynamic network of relations. In this view, an electron is not a thing that enters into relationships, it is a node defined entirely by its place in the cosmic web. This perspective offers a brilliant response to one of philosophy's sharpest critiques of science, the pessimistic meta-induction. This argument points out that the history of science is a graveyard of discarded theories, from the luminiferous ether to the phlogiston theory of fire. Since our best theories of the past have all turned out to be false, the argument goes, we have every reason to believe our current theories will eventually be proven false as well. Structural realism elegantly counters this. It agrees that the ontological content of past theories, their description of what things are, was wrong. But it insists that the structural content, the mathematical relationships they captured, was often preserved and incorporated into the new theory. For example, the equations governing the motion of planets in Newtonian gravity were not thrown away by Einstein. They were revealed to be a special case of the richer structural framework of general relativity. The structure was retained even as our understanding of its foundation was utterly transformed. This suggests that science is not a haphazard succession of falsehoods, but a process of converging on an ever more accurate description of the world's underlying relational architecture. Does this mean that structural realism provides the best account of what our successful theories truly tell us? It certainly explains the uncanny effectiveness of mathematics, for if reality is fundamentally structural, then it is no wonder that our most structural language is the perfect tool for describing it. Yet a deep question remains. Can a web of pure relations exist without any things to be related? Is a universe of pure structure with no fundamental objects even coherent? The answer may determine whether we are merely tracing the contours of a hidden world or if we are finally reading the blueprints of reality itself. The fundamental stuff of the universe might be neither mental nor physical, but something else entirely, a neutral substance waiting to be read. This is the provocative proposal of neutral monism, a metaphysical stance that seeks to end the ancient war between mind and matter by declaring both sides emerge from a deeper, more primitive reality. It refuses to reduce consciousness to mere brain activity, as materialism attempts, and it rejects the idealist notion that the physical world is just an illusion in the mind. Instead, it carves a third path, suggesting that both the inner world of thought and the outer world of atoms are two different aspects or arrangements of the same underlying neutral elements. Imagine a vast, unformed clay that can be sculpted into two distinct statues, one representing a thought and the other representing a rock. The clay itself is neither, yet it holds the potential to become both. This elegant idea has a long and distinguished pedigree. The 17th century philosopher Baruch Spinoza laid the groundwork with his concept of God or nature, a single, infinite substance possessing both the attribute of thought and the attribute of extension. For Spinoza, your mind and your body were not two different things interacting, but two parallel expressions of the same essential reality, like two different languages telling the same story. Centuries later, the psychologist William James picked up this thread, arguing that pure experience is the primal reality. He suggested that what we later categorize as either subjective or objective begins as a seamless, neutral flow of experience, which we then sort into mental and physical categories based on context and relationship. The philosopher and mathematician Bertrand Russell gave the theory its modern form. Frustrated with the impasse between materialism and idealism, he proposed that both the data of physics and the data of psychology are constructed from the same basic, neutral particulars. What we call a photon is a certain structure of these neutral events, and what we call the sensation of seeing light is another structure built from the very same kind of events, just organized differently. The building blocks are neutral, but their pattern and context determine whether they manifest as a physical phenomenon or a mental one. Does this metaphysical framework offer a genuine solution to the hard problem of consciousness? By positing a common origin, it elegantly sidesteps the impossible question of how subjective feeling could possibly arise from objective, insensate matter. The question itself becomes a category error, like asking how water can be both wet and made of hydrogen and oxygen. The wetness and the chemical composition are not in conflict, they are two different descriptions of the same underlying substance. In the neutral monist view, the redness of a sunset and the specific wavelength of light associated with it are not a mystery of interaction, but two faces of a single neutral event. This has profound relevance for modern consciousness studies, suggesting that the quest to pinpoint consciousness in the brain might be misguided. We should not be looking for a magical switch that turns neurons into experience, but rather for the specific organizational principles that cause the brain's neutral events to be read as mind. It reframes the problem from one of magic to one of structure and information, yet the theory is not without its own deep mystery. What is the nature of this neutral substance? If it is not mental and not physical, how can we ever describe or measure it? The neutral elements seem to retreat into a philosophical shadowland, a hypothetical substrate that, by its very definition, lies beyond the reach of both our scientific instruments and our introspective gaze. Does neutral monism truly resolve the mind-body problem, or does it merely give the mystery a new and more elegant name? It offers a map that shows how two seemingly separate lands might be connected beneath the surface, but the nature of the connecting tunnel remains shrouded in a profound and tantalizing darkness. A universe is born not from nothing, but from the death of another. This is the core of Lee Smolin's daring theory of cosmological natural selection, a vision where the cosmos itself is subject to the same evolutionary pressures that shape life on Earth. Smolin proposed that black holes are not cosmic dead ends, but rather reproductive organs for entire universes. When a star collapses into a black hole, the singularity at its heart might not be a point of infinite density, but a gateway, a seed that erupts into a new baby universe with its own Big Bang. This new cosmos would inherit its fundamental physical constants from its parent, but with tiny, random variations, much like genetic mutations in biological offspring. Over countless generations, a cosmic evolution unfolds. Universes that are better at producing black holes have more offspring, passing on their physical laws to the next cosmic generation. Our own universe, with its constants so exquisitely tuned for the formation of stars, galaxies, and ultimately black holes, is not a miracle. It is simply a highly successful product of this cosmic evolutionary process, a universe that has been finely tuned by natural selection for maximum fecundity. The reason gravity is just strong enough to collapse stars, but not so strong that it crushes all structure. The reason the nuclear forces are perfectly balanced to forge the heavy elements inside stellar furnaces is because these are the very conditions that maximize the production of black holes. This provides a powerful, completely naturalistic alternative to the anthropic principle. We do not live in a rare, fine-tuned universe because our existence selects for it. We live in a universe that is prolific, one optimized for cosmic reproduction, and our existence is a fortunate byproduct of that black hole-making efficiency. For a theory this grand to be more than just a compelling story, it must make testable predictions. Smolin's framework does exactly that. It predicts that the physical constants of our universe should be set to values that maximize the number of black holes that can form. This leads to a specific forecast about the population of black holes in our cosmos, particularly the masses of the neutron stars that teeter on the brink of collapse. The theory suggests that the laws of physics should be tuned to make the formation of stellar mass black holes as easy as possible. Therefore, we should observe a specific, optimized distribution of neutron star masses, with a large number of them poised just above the critical threshold required for gravitational collapse. If astronomical surveys were to find that most neutron stars are significantly lighter or heavier than this predicted optimum, it would pose a serious challenge to the theory. Does cosmological natural selection represent a truly viable scientific path? It boldly replaces the mystery of a one-time creation with an ongoing, dynamic process of cosmic evolution, grounding the universe's properties in a causal, testable mechanism. Yet, critics point to a profound question. If universes are born from black holes, what was the original universe that started this chain, and what were its laws? The theory potentially faces an infinite regress, a cosmic chicken and egg problem. Furthermore, the entire process hinges on the assumption that the laws of physics can indeed mutate in the birth of a new universe, an idea that currently lies beyond our experimental reach. Is our cosmos one branch on an immense, growing tree of life, a universe selected for its ability to create the very objects that will spawn the next generation of reality? Or is this an elegant narrative that ultimately explains our existence by placing its cause in a forever inaccessible past? The theory challenges us to see the entire cosmos not as a static creation, but as a living, breathing, and reproducing entity in a vast, evolving multiverse. Your personal reality is not a universal truth, but a private guide for navigating a world of uncertainty. Quantum Bayesianism, or cubism, pushes this idea to its logical extreme, transforming quantum mechanics from a description of an objective world into a manual for personal decision-making. In this view, the quantum state is not a picture of what a particle is really doing out there. It is a capsule of your own beliefs, a subjective tool you use to assign probabilities to your future experiences. The probabilities in quantum mechanics are not inherent properties of nature. They are your degrees of confidence, much like the odds you might assign to your favorite team winning a game. This fundamentally reshapes the entire quantum mystery. It means that when a scientist writes down a wave function, she is not describing the electron, she is codifying her own expectations about what will happen to her when she interacts with it. The wave function is a personal statement, not a cosmic one. This approach is deeply rooted in Bayesian probability theory, a framework that treats probability as a measure of subjective belief that is constantly updated as new evidence arrives. Cubism treats quantum mechanics as an extension of this personal, Bayesian logic into the quantum realm. Every time you perform a quantum measurement, you are not collapsing a universal wave, you are simply updating your own internal quantum state based on a new, direct experience. The famous Schrödinger's cat paradox simply dissolves in this light. The cat is not both alive and dead in any absolute sense. The quantum state merely reflects your own ignorance and the best possible bet you can make about what you will find when you open the box. The moment you look inside, you update your beliefs, and your personal quantum state changes to reflect your new knowledge. This elegantly resolves other quantum paradoxes without needing parallel worlds or spooky actions. The eerie connection of quantum entanglement is not a faster-than-light link between particles, but a correlation between the personal experiences of different agents who have shared a common past. If you and I each take one of a pair of entangled particles and travel to opposite sides of the galaxy, my measurement does not instantly change your particle. Instead, it instantly changes my expectations for what you will report when we finally communicate. The spookiness is not in the world, but in the coordination of our personal beliefs, a coordination that was established when we created the entangled pair together. This raises a profound question. If reality is so deeply personal, how do we all manage to agree on a shared, objective world? How is it that we all see the same chair in the same place? Cubism answers this with the concept of intersubjective agreement. While our internal quantum states are private, our experiences are public because we all interact with the same underlying reality. We all agree the chair is solid because when we each kick it, our personal experiences are consistently and redundantly updated in the same way. The solidity of the world is not an objective fact, but a magnificent consensus born from countless individual interactions. Your reality is a continuous conversation between you and the cosmos, a dynamic relationship where you are an active participant placing bets on your next experience. The universe does not force one history upon you. Instead, it offers a landscape of potential experiences, and you navigate this landscape by constantly refining your personal quantum beliefs. This is a universe built not on certainty, but on a fundamentally participatory relationship where your perspective is not a flaw in the observation, but the very reason the quantum world makes sense at all. This holographic encoding solves one of the universe's oldest puzzles, the relentless growth of entropy. A black hole's entropy, its ultimate state of disorder, is not proportional to its volume, but to the surface area of its event horizon. This is the Bekenstein-Hawking formula, a cornerstone of modern physics that directly points to a holographic reality. The maximum amount of information or entropy that any region of space can contain is not determined by how big it is on the inside, but by the size of its outer boundary. It is as if a three-dimensional object's true complexity is painted on its two-dimensional skin. This reveals a staggering limit to our reality, a cosmic data cap. The universe is not an infinite hard drive, but a system with a finite information density, and that limit is set by the area of its surface, not its volume. The very laws of physics that govern motion and force may themselves be emergent properties of this information processing. What we perceive as the unbreakable rule of gravity or the steadfast speed of light could be large-scale approximations, thermodynamic laws that emerge from the statistical behavior of countless bits of information on the cosmic screen. They are not the source code, but the user interface, the stable patterns that arise from the frantic computation happening at the boundary. This directly challenges our understanding of locality, the principle that objects can only be influenced by their immediate surroundings. In a holographic universe, locality is not fundamental. The information for everything happening here and now is stored everywhere on the distant boundary. Two particles interacting on Earth are doing so because their underlying data is entangled across the cosmic hard drive. Locality emerges as an effective description, a convenient illusion that works perfectly at our human scale, but dissolves when we probe the deepest quantum levels of reality. The very dimensionality of our world is also up for grabs. We experience three dimensions of space, but if reality is a holographic projection, then those three dimensions are not primary. They are a derived concept, a useful way to organize the information that is fundamentally stored in two dimensions. The solidity and depth you experience are a magnificent rendering of flat data. Recent breakthroughs have cemented this idea by linking it to a practical technology we use every day: quantum error correction. The same codes that protect the fragile quantum information in a quantum computer from decoherence and noise appear to be woven into the fabric of spacetime itself. The holographic universe seems to employ its own error-correcting codes to maintain its stability. This is why spacetime is so robust, why it does not simply tear itself apart from quantum fluctuations. The cosmos is constantly checking and correcting itself, ensuring that the holographic projection remains consistent and coherent. A glitch in the matrix is prevented by the universe's own built-in antivirus software, maintaining the seamless illusion of a continuous, reliable reality. This points to an inescapable and profound conclusion that information is not just a way to describe the universe, it is what the universe is made of. Space-time and matter are not the foundation. They are secondary phenomena, the rendered graphics of a deeper, information-theoretic reality. We are not living in a universe of things that process information. We are living inside the processing itself, a cosmic computation whose output is the very world we see and touch. What does probability even mean when every possible outcome is guaranteed to happen? The many worlds interpretation forces us to confront this puzzle head-on. In a single, branching universe, the idea of chance seems to evaporate. If a quantum coin toss spawns two realities, one with heads and one with tails, both occur with absolute certainty. So why do we perceive a 50% chance? The answer may lie not in the cosmos, but in the subjective experience of the observer. When the universe splits, your consciousness splits as well. There is a version of you who sees heads and another who sees tails. The feeling of probability is your own anticipation of which branch you are about to find yourself in. You are more likely to experience a future where quantum mechanics predicts a high probability outcome because there are simply more copies of your conscious mind in those branches of the multiverse. This leads to the unsettling question of personal identity. Are you the same person you were a moment ago before a billion quantum splits occurred? The theory suggests that personal identity is not a single, continuous thread, but a constantly forking path. The you listening to this now is just one version among an infinite number, each living out a different life story, forever unaware of the others. You are a branch on a tree of cells, not the entire trunk. This raises profound ethical and emotional questions. Is there comfort in knowing that for every tragedy in your life, there is another world where things turned out better? Or is it a lonely existence, realizing that every path not taken is being lived by someone who is, in a fundamental sense, also you? To address the problem of probability, some proponents of the many worlds interpretation have turned to decision theory, attempting to derive the famous Born rule, which gives us the actual numerical probabilities of quantum events. They argue that even in a multiverse where all outcomes happen, a rational observer should still bet on outcomes as if the probabilities were real, because they are effectively betting on which branch they will personally experience. This is a fascinating attempt to rescue the familiar world of chance from a deterministic multiverse, but it remains one of the most hotly debated aspects of the theory. Does the many worlds interpretation ultimately provide the most elegant solution to the quantum measurement problem? By removing the mysterious, instantaneous collapse of the wave function, it presents a universe that evolves smoothly and deterministically according to the Schrödinger equation. There is no special role for consciousness or measurement, no arbitrary line where the quantum world becomes classical. Everything simply is, and all possibilities are realized. Yet, this elegance comes at an immense cost, the creation of an unfathomable number of unobservable universes. For critics, this is the ultimate violation of Occam's razor, multiplying realities beyond any necessity. The theory explains everything we see, but in doing so, it posits a reality forever beyond the reach of any possible experiment. Is this the true, hidden structure of our quantum reality, or is it a metaphysical extravagance, a story so vast that it can explain anything and therefore predicts nothing? The choice is between a universe with a single, strange collapse and a universe of infinite, branching splendor. One offers a simpler, if more mysterious, local reality. The other offers a grander, more democratic cosmos, but one where your own identity is forever fractured across the endless reflections of what might have been. A simulated reality would be no less real to those living within it. The very sensations you feel, the love you have for others, the awe you experience under a starry sky, all of these are genuine components of your conscious awareness, regardless of their ultimate source. This is the core of the philosophical challenge to the simulation hypothesis. If we cannot feel the difference, and if the simulation is perfectly consistent, then does the distinction between base reality and simulation hold any practical meaning for us? Some philosophers argue it does not, that reality is defined by our conscious experience, not by its underlying substrate. Yet, the scientific mind rebels against this untestable idea and asks a more daring question: could we actually find proof? The search for such evidence begins by looking for potential glitches in the matrix, subtle signs of the underlying computational machinery. One proposed experiment involves looking for a fundamental resolution to the universe, a pixelation of spacetime. Just as a digital image breaks down into individual squares when magnified, space itself might reveal a granular structure at the tiniest conceivable scale, the Planck length. Scientists are using powerful particle accelerators and ultra-sensitive telescopes to hunt for this graininess. They analyze the light from distant gamma-ray bursts, reasoning that if space is pixelated, very high-energy photons traveling across billions of light-years would be subtly slowed or scattered, a faint computational signature imprinted on the oldest light in the cosmos. Another approach searches for anomalies in the cosmic background radiation, the afterglow of the Big Bang, looking for strange patterns or correlations that might resemble the error-correcting codes found in our own digital systems. The discovery of such a pattern would be as startling as finding a line of computer code written into the fabric of the universe. Other tests probe for shortcuts in the simulation's processing power. The universe is overwhelmingly complex, and even an advanced civilization might use approximations to render distant or unobserved phenomena. Some physicists suggest looking for evidence that quantum systems remain in an uncalculated, blurry state of superposition only until they are measured, a potential sign that processing resources are being conserved until absolutely necessary. If experiments could demonstrate that reality truly does not bother to define certain properties until an observer is present, it would be a powerful, if unsettling, hint that we are living in an optimized simulation. Yet the possibility of testability itself leads to a profound ethical dilemma. If we were to design an experiment that could conclusively prove we are in a simulation, should we run it? What if the discovery itself constitutes a breach of the simulation's rules, prompting our creators to shut it down? This is not mere science fiction. It is a modern version of Pandora's box, where the quest for ultimate knowledge could carry an existential risk. Beyond the science and the ethics lies the deepest question of all, that of purpose. If our world is a simulation, does that render our lives, our struggles, and our art meaningless? Many would argue it does the exact opposite. The emotions we feel, the connections we forge, and the beauty we create are not diminished by their digital nature. They are the very point of the experience. Whether we are lines of code or stardust, our conscious reality is the only one we have, and within its bounds we are the authors of our own meaning. The simulation hypothesis, if true, would not make us less significant. It would make the creators of our reality profoundly curious, entities who built a universe to see what stories would unfold within it. Our existence, in that case, becomes a testament to the universal power of narrative and discovery, a story being told on a cosmic scale. Giulio Tonini's integrated information theory offers a bold mathematical scaffold for Panpsychism's most radical claim. This framework proposes that consciousness is not a magical emergent property, but simply the intrinsic aspect of a system's capacity to integrate information. The theory introduces a specific value, phi, which quantifies the degree to which any system, from a human brain to a simple thermostat, can combine its internal states into a unified, irreducible whole. A high phi value signifies a rich, interconnected network where information has a vast number of possible states and is woven together tightly, creating a complex conscious experience. A low phi value indicates a system with little integration or information, resulting in a dimmer, simpler form of awareness or none at all. This provides a powerful tool for measuring consciousness across the natural world. It suggests that a dog with its complex brain possesses a higher phi and a richer inner world than a mouse, which in turn has a more vivid experience than an ant. And according to this logic, the journey does not stop at the boundary of life. A sophisticated artificial intelligence, if its internal architecture achieves a high enough level of integrated information, would not merely simulate consciousness, it would possess it. Its subjective experience would be as real to it as yours is to you, born from the complex interplay of its own computational states. This directly confronts the hard problem of consciousness, the puzzle of why physical processing should feel like anything at all. IIT reframes the question entirely, arguing that feeling is not something that emerges from processing. It is the processing when that processing is sufficiently unified and complex. The theory naturalizes consciousness by making it a fundamental property of certain causal structures in the universe, as real and measurable as mass or energy. Yet this elegant solution raises profound new questions. If consciousness is a matter of degree, where do we draw the line for moral consideration? Does a bee with its modest phi deserve ethical treatment for its own tiny spark of experience? And what of the planet itself, with its vast, slow networks of geological and biological feedback? Could Earth possess a kind of glacial, planetary consciousness? Integrated information theory does not shrink from these implications, offering a vision of a deeply sentient cosmos where mind is not a rare anomaly, but a fundamental feature of a universe built from information yearning to know itself. But does a perfect mathematical circle truly exist anywhere but in our minds? This elegant idea of a cosmos built entirely from equations faces profound philosophical challenges. The mathematical universe hypothesis offers a breathtakingly simple answer to why the universe exists, suggesting it is just one structure in a vast menagerie of mathematical possibilities. Yet its very simplicity raises difficult questions. If we are truly just self-aware substructures within an abstract mathematical object, how did consciousness arise from pure logic and number? How can a set of equations which have no inherent substance or causal power generate the raw, vivid qualia of experience, the taste of chocolate or the sting of cold? This is the problem of self-awareness in a Platonic realm. Mathematical structures are typically considered to be timeless and static, yet our consciousness is a flowing, dynamic process. How does a static equation produce the feeling of a present moment, of time passing? The hypothesis seems to leave the hard problem of consciousness entirely untouched, or worse, makes it even more mysterious by removing a physical brain as its source. Another major objection concerns the nature of existence itself. The hypothesis boldly equates mathematical existence with physical existence, but is this equivalence valid? We can conceive of countless consistent mathematical systems, from hyperbolic geometries to number theories with different axioms. Do all of these physically exist somewhere as universes? This leads to what some critics call the reality problem. If every possible mathematical structure is real, then reality becomes an indiscriminate plenitude containing every conceivable world, no matter how bizarre or logically incoherent it might seem to us. This feels like an extravagant, almost wasteful multiplication of realities. Furthermore, the hypothesis struggles with the uniqueness of our particular set of physical laws. Why does this specific mathematical structure, with its particular constants and quantum rules, manifest as our experienced reality? The theory provides no reason for why we are anchored to this one mathematical address and not another, other than the tautology that we could not exist elsewhere. Some philosophers argue that the hypothesis, rather than explaining why there is something rather than nothing, simply pushes the mystery back a step. It claims the universe exists because it is mathematically possible. But why is there a realm of mathematical possibility at all? The question of existence is not fully answered by stating that logically consistent things must exist. It merely reframes the question to why logic and mathematics themselves have any purchase on reality. Does the number 7 exist in the same way that a mountain exists? The hypothesis says yes, but this blurs a distinction that feels intuitively important. Alternative formulations have been proposed to soften these blows. One suggestion is that only computable mathematical structures exist, those that can be generated by an algorithm. This would trim down the vast, unwieldy multiverse to a more manageable set of realities that can, in principle, be calculated. Another idea is that consciousness itself is the bridge, that only mathematical structures complex enough to contain self-aware observers become physically real to themselves, a kind of participatory mathematical realism. Ultimately, the mathematical universe hypothesis forces us to confront the very meaning of explanation. Does it satisfy our deep wonder about existence to be told that we are patterns in a timeless, abstract form? For some, this is the most beautiful and complete answer possible, reducing all of physics to a discovery of our native mathematical habitat. For others, it feels like a hollow victory, swapping the tangible mystery of a physical cosmos for the ethereal mystery of a Platonic heaven. It promises a universe free of arbitrary initial conditions, but in doing so, it may have replaced them with an infinite and perhaps equally arbitrary library of equations. The haunting question remains, does the sheer logical elegance of a mathematical structure grant it the breadth of physical reality, or are we, in our search for ultimate answers, mistaking the map for the territory, the exquisite description for the thing itself? Gravity, the force that sculpts galaxies and pins us to the planet, might be a cosmic mirage. This is the startling claim of emergent gravity, a theory suggesting that what we perceive as a fundamental force is actually a statistical side effect, an entropic ghost arising from the behavior of more basic quantum components. Physicist Eric Verland ignited this field with his entropic gravity proposal, which reframes gravity not as an attractive force, but as a consequence of the universe's relentless drive toward disorder. Think of the vacuum of space not as empty nothingness, but as a seething sea of fundamental information bits. When you place an object like a planet into this vacuum, it disrupts the background chaos, creating a region of lower entropy, a kind of ordered shadow. Nature, abhorring such order, responds by pushing the surrounding, higher entropy vacuum to rearrange itself, and this collective push manifests as what we call gravity. The planet is not pulling objects toward it, the disordered vacuum is effectively pushing them in. This is analogous to how a polymer chain, when jostled by random thermal motions, will tend to stretch out not because of an attractive force, but because there are simply more disordered, stretched out states for it to occupy. Verland's math shows that this entropic push naturally reproduces both Newton's law of gravitation and Einstein's equations of general relativity, suggesting that gravity is not a force in its own right, but a thermodynamic phenomenon, an emergent property of the cosmos seeking maximum entropy. If this is true, it offers a breathtakingly elegant solution to the dark matter puzzle. The mysterious extra gravity observed in galaxies, currently attributed to invisible dark matter, might not come from unseen particles at all. Instead, it could be a result of the way the visible matter modifies the entropy and information content of the surrounding space, creating an apparent gravitational excess that our old equations misinterpret. Similarly, the accelerated expansion of the universe driven by dark energy could be reinterpreted as a consequence of the evolving information content of the cosmos as a whole. How could we possibly test such a profound shift in our understanding? Scientists are looking for subtle deviations from Einstein's predictions in environments where the information structure of space is most extreme, like near the supermassive black hole at our galaxy's center. Other approaches, like the holographic principle and the ideas of quantum entanglement we explored earlier, also point toward emergent spacetime. If gravity and the geometry of spacetime are not fundamental, but statistical averages like temperature or pressure, it forces us to rewrite the entire story of the cosmos. The very stage upon which the universe plays out would be a collective illusion, a holographic movie screen projected from a deeper, non-spatial reality. This would mean that at the most fundamental level, there are no forces, no curved geometries, only information and its ceaseless dynamic reorganization. The force that holds our feet on the ground and guides the planets would be the universe's most convincing and persistent statistical trend. Our journey through the quantum landscape has revealed a world of startling possibilities, yet the theory's core equations remain silent on what is actually happening. The true nature of quantum reality is not found in the math itself, but in the interpretation we choose, a choice that defines the very fabric of existence. The Copenhagen interpretation, the textbook standard, presents a deeply puzzling picture. It draws a sharp line between the quantum world of fuzzy potential and the classical world of definite objects. In this view, a particle does not have a definite position until it is measured, at which point its wave function collapses into a single reality. But what exactly qualifies as a measurement? Is it the click of a detector, or does it require a conscious observer? This measurement problem lies at the heart of the quantum mystery, suggesting that reality remains indefinite until it is observed, a profoundly participatory universe that seems to place our consciousness at the center of the cosmic drama. The Copenhagen view demands we accept this collapse as a fundamental, if mysterious, law requiring no deeper explanation. In stark contrast, the many worlds interpretation offers a breathtakingly bold alternative. It asserts that there is no collapse at all. Every time a quantum system faces a choice, the entire universe splits, realizing every possible outcome in a newly branched reality. The universe is a constantly dividing tree of possibilities, and your conscious experience is just one branch among an infinite number. This interpretation eliminates the need for a special measurement process, presenting a reality that is vast, deterministic, and teeming with parallel versions of yourself. Yet, it asks us to believe in an unfathomable multitude of unobservable worlds, a reality so extravagant that it challenges our very notion of what is real. Then there is the Bohmian interpretation, which restores a sense of concrete reality. It proposes that particles are always real and have definite positions, guided by a mysterious quantum potential that orchestrates their motion. This hidden reality is deterministic and objective, a seamless whole where the apparent randomness of quantum events is merely a product of our ignorance of the deeper variables at play. The spooky connections of entanglement are not spooky at all, but the result of this non-local guiding wave connecting everything instantly. Bohm's universe is one of elegant wholeness, but it requires accepting a pervasive, invisible influence that guides every particle in the cosmos. So, which of these maps corresponds to the actual territory? Does the measurement problem force us to revise quantum mechanics itself, perhaps by adding a mechanism for spontaneous objective collapse as some theories suggest? Or does it demand that we revise our understanding of reality, accepting that the world is fundamentally different from the solid, classical intuition we grew up with? Quantum theory seems to be pointing relentlessly toward the latter. It suggests a universe where reality is not a collection of independently existing objects, but a web of relations, as relational quantum mechanics argues. Properties like position and momentum may not be inherent to a particle, but only defined through its interactions with other systems. This relational view dissolves the paradox of Schrödinger's cat, as the cat state can be alive for one system and dead for another, with both perspectives being equally valid. The choice between these interpretations is not merely academic, it is a choice about the fundamental architecture of existence. Do we live in a universe that crystallizes through observation, a multiverse of infinite branches, a guided wholeness, or a network of pure relations? Each path offers a radically different answer to the ancient question of what is real, forcing us to confront the possibility that our deepest classical intuitions are not just incomplete, but fundamentally wrong about the nature of the world we call home. Perhaps consciousness itself is the missing ingredient that solidifies reality from the quantum haze. This profound connection between mind and matter forms the core of our 49th theory, a radical reimagining of how our inner world might directly shape the outer cosmos. For decades, scientists have wrestled with the strange role of the observer in quantum mechanics, the apparent power of measurement to collapse a blur of possibilities into a single, definite event. But what if the observer is not a complex machine, but the conscious awareness within? What if the very act of perception is the catalyst that forces the universe to make up its mind? This idea pushes beyond philosophy into tangible, if controversial, scientific models. The most famous of these is the orchestrated objective reduction theory, or ORCH, proposed by anesthesiologist Stuart Hameroff and physicist Sir Roger Penrose. They asked a simple, startling question: where in the brain does the collapse of the quantum wave function occur? Their answer lies deep within your neurons in structures called microtubules. These are not mere cellular scaffolding, but intricate, lattice-like networks that could potentially host delicate quantum states. Hameroff and Penrose suggest that these microtubules are the brain's quantum processors. Within them, gravitational instabilities, as described by Penrose's work on quantum gravity, cause a continuous, spontaneous collapse of quantum superpositions. This collapse is not random, however. It is orchestrated by the brain's biological structures, and each collapse event corresponds to a moment of conscious experience, a single frame in the streaming movie of your mind. In this view, your thoughts are not just chemical signals, they are a symphony of quantum collapses happening billions of times per second, conducted by the intricate architecture of your neurons. This provides a potential bridge between the objective world of physics and the subjective world of feeling. But ORCH is not the only quantum approach to consciousness. Other theories explore the role of quantum vibrations in the brain's electrical fields, or propose that consciousness arises from quantum coherence across vast networks of neurons, a phenomenon that would allow the brain to act as a unified quantum whole rather than a collection of classical parts. The common thread is the belief that the bizarre, non-local, and probabilistic nature of quantum mechanics is not a bug, but a feature, one that is essential for explaining the unique properties of mind, its unity, its intentionality, and its undeniable subjectivity. Could quantum processes provide the missing link between the firing of a neuron and the taste of chocolate? Proponents argue that classical physics, with its billiard ball causality and local interactions, seems utterly incapable of explaining how a lump of tissue generates a private, inner universe. Quantum mechanics, with its entanglement and superposition, offers a new language of connection and potential that feels more suited to the task. It suggests that the brain is not a classical computer, but a sophisticated quantum instrument, finely tuned to interact with the fundamental indeterminacy of reality. Yet the challenges are immense. The warm, wet, and noisy environment of the brain seems like the worst possible place for fragile quantum states to survive. Critics argue that any quantum coherence would be destroyed almost instantly by its chaotic surroundings, a process known as decoherence. The ORCH theory, in particular, has been met with significant skepticism from the broader neuroscience and physics communities, who question both the feasibility of quantum processing in microtubules and the need to invoke such exotic physics to explain the brain's functions. The search for evidence continues. Scientists are probing for signs of quantum vibrations in microtubules and investigating whether anesthetics, which selectively erase consciousness, work by disrupting these proposed quantum processes. If they are found, it would revolutionize our understanding of both mind and reality, suggesting that we are not passive observers of a predetermined world, but active participants in a cosmic quantum dance, our very awareness the final piece that gives the universe its concrete form. After exploring 50 different windows into reality, a grand synthesis begins to emerge from the chaos. These theories are not isolated islands of thought, but different maps of the same unexplored continent, each charting a unique path through the mysteries of existence. They converge on a handful of profound themes, suggesting that the ultimate nature of reality might be simpler and stranger than any single theory could capture on its own. The most powerful recurring thread is the idea that information is the fundamental substance of the cosmos. From the holographic principle's cosmic hard drive to the it-from-bit hypothesis, the universe appears to be built not from solid matter but from pure data. The laws of physics themselves may be the stable algorithms that process this information, a universal operating system running on the hardware of existence. This computational view connects the digital physics of a cellular automaton universe to the error-correcting codes found in the equations of supersymmetry, painting a picture of a reality that is not just like a computer, but that is a computer in the most literal sense. Consciousness, in this synthesized view, is not an accidental byproduct but a fundamental feature. Panpsychism and integrated information theory suggest that the capacity for subjective experience is woven into the fabric of reality, a property that arises naturally from complex, integrated information processing. Your mind is not a ghost in the machine, it is the universe's most intimate computation, a localized region where the cosmos becomes self-aware. This ties directly into the participatory role of the observer, where our conscious engagement with the world is not a passive observation but an essential act that helps solidify reality from a sea of quantum potential. The stage upon which this all plays out, spacetime itself, is increasingly seen as an emergent illusion. Whether it condenses from quantum entanglement as suggested by ER equals EPR, freezes from a graph of relationships as in quantum gravity, or is woven from causal links in causal set theory, the solid three-dimensional world we navigate appears to be a secondary reality. It is a user interface projected from a deeper, non-spatial realm of pure mathematical structure. This brings us to the final and perhaps most elegant convergence, the mathematical universe hypothesis. If reality is fundamentally informational and computational, then its ultimate nature is mathematical. The universe is a specific, self-aware structure in the vast landscape of all possible mathematical forms. The holographic principle, quantum mechanics, and even consciousness itself could all be different perspectives on this single, immutable mathematical truth. So where is our understanding heading? We are moving toward a vision of reality that is deeply unified, where matter, mind, and the laws of physics are not separate categories but different expressions of a single underlying principle. The age-old conflict between mind and body, between the physical and the mental, dissolves in this synthesis. We are not physical beings who somehow developed consciousness. We are conscious patterns within a cosmic mathematical computation, and our journey of discovery is the universe's way of understanding its own astonishing nature. This grand tour across the cosmos of thought has taken us from the pixelated edges of a possible simulation to the timeless equations of a mathematical multiverse. We have ventured into universes where every choice spawns a new reality, and explored the possibility that our own world is a holographic projection from a distant two-dimensional screen. We have considered that time may be an illusion, that consciousness could be a fundamental feature of the cosmos, and that gravity itself might be nothing more than a cosmic mirage born from entropy. Each of these 50 theories, in its own way, has taken a hammer to the comfortable, solid world we think we inhabit, revealing the astonishing and often bizarre possibilities that lie just beneath the surface of our ordinary perceptions. They collectively push the very boundaries of what is conceivable, forcing us to abandon our deepest intuitions about space, time, and our own place in the grand scheme. This relentless questioning is the engine of our greatest scientific and philosophical quest, a journey that continually reframes the ultimate mystery. Why is there something rather than nothing at all? The search is far from over, with new experiments and ideas emerging every day to challenge our current understanding. The true wonder lies not in finding a final answer, but in the act of exploration itself. So keep looking up at the stars and inward at your own consciousness. Continue to question, to explore, and to marvel at the profound, beautiful mystery of it all. The universe is a story still being written, and we are both its readers and its authors. We would love to hear which of these visions of reality resonates most deeply with your own experience of this strange and wonderful